Sound check for Elliot. Can Elliot hear this? Elliot, come in. We need you. All right. Tell me when. Test, test. Elliot, can you hear this? And remote students, can you hear this?
One, two, three, 4, 5. Is that good?
Do you need me to go more, or are you good? Okay. Thanks, Evan, for letting me know the sound is working. Elliot, can I just get started? I don't need to click record or anything, do I? That's all. Excellent. Okay, so welcome everybody to Cryptography. We're going to be talking about this, but not so much software security, which is an interesting distinction I want to make. What is cryptography, by the way? Anybody out there? And please use our friend Mike, who's on a pillow now, because we lost the mic stand.
Systems for encoding and decoding data?
Systems for encoding and decoding data. Before you sit down again, what do you mean by encoding and decoding data then?
So representing the same data in a different way, which may be hard to decrypt for somebody without that special tool.
Yeah, okay, cool. Yeah, excellent. So it actually, cryptography, it often includes itself and cryptanalysis, but that's technically cryptology. It includes both of these. But the idea is cryptography is secret keeping. And it's secret keeping through encoding. And cryptanalysis is code breaking instead of code making. And it's secret revealing. Interestingly enough, this is not Jedi versus Sith kind of thing. Like the cryptography is not the good guy thing and cryptanalysis the bad guy thing. So cryptanalysis actually has use cases beyond just computer science. You can, as a cryptanalysis, you can actually study dead languages and try to understand where they came from. Because the same tools that you use to decode what appear to be random messages that were sent by two parties are the same principles you use to decode a language that you don't understand. So it's kind of cool that way. And also, of course, it matters whether you think secrets should be kept or not, whether you think these are good or bad. But I do want to point that out. It's not good versus bad. I also want to talk about what cryptography isn't. I sort of touched on this, but it isn't software security. It's important for software security, just like walls are really important if you have a castle and you don't want people to storm your castle. But walls are not the same as castle defense. You need them, right? And you need people who can maintain them, but castle defense is more than just having really strong walls. That make sense? Cool. Awesome. And we're going to probably touch on software security sometime over a break. So this will be kind of the foundations for that. And then sometime over break, I'm going to lead something on web security. And here's the general day. We're going to talk about randomness, hashing, and encryption, as well as we're going to get to asymmetric key encryption, which is pretty cool. It's called RSA. And then we might touch on a couple deeper topics. This is the general workshop outline, too. You all are going to be building some random stuff, like literally some random stuff. You're going to be building a hashing algorithm. You're going to be building 3 different encryption algorithms. That's the gist of today. There's a big asterisk here, which is don't try this at home. Do you know why I'm saying that? OK, cool. It's more like don't use this in production is what it should really say there. Like, we're going to be building these things, but like, please, more than any other CS library, please don't use these. Because like, cryptography is definitely not something you want to get wrong. So like, don't after this be like, oh, cool, I have my own RSA encryption. I'll use that instead of the actual like out there RSA encryption. Cool. And I also want to point out that like if you get nothing else out of today, remember that cryptography is kind of these three things at this point. It talks a lot about randomness, talks a lot about hashing, and a lot about encryption. So we're going to cover a lot of conceptual stuff upcoming and then get more and more specific as we go. What is randomness? Anybody? Just blurt it out. Well, to Mike. Try blurting out a random sequence if you want.
Unpredictability?
Unpredictability. OK, cool. So Urban Dictionary doesn't really agree with you, but that's OK. I like your definition better. So randomness for us is really going to be more about something being unpredictable. And that also means that the output is uniformly distributed. So if you've got a bunch of possible random outputs, you want them to appear as frequently as each other. And it's also this stuff, that the next is unrelated to the previous, and the next is unrelated to the previous, and all the numbers that you might ever generate are unrelated to each other. There's no way that you could figure out one from the other. And that's randomness in general, but we also care about random number generators. We care about random number generators so that we can have random numbers, which makes a lot of sense for situations like cryptography, but also for games or just for fun. Maybe you just want to sit there and generate random numbers. I do that sometimes. I'm not weird. So I have a small game here, or challenge, which is which of these coin tosses is more likely? We toss one coin, we get 0. We toss one coin, we get 1. Who thinks the blue is more likely? Who thinks the red is more likely? OK, cool. Who thinks something else? And say it to Mike. Yeah.
They have a 50-50 shot.
50-50 shot. OK, cool. All right, let's look at 10 coin tosses now. So here are 10 coin tosses. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and this one is 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. OK, who thinks the blue is more likely? Who thinks the red is more likely? Cool. Who has a different opinion? Yes.
They're still the same.
They're still exactly the same. Yeah. So this is something very, very weird when we think about randomness. You can't like pick an arbitrary number and say it's more random than some other number. They're both sort of equally random in this awkward sense. So you're just as likely to get 10 zeros as you are this exact sequence we have listed here. So both of these actually just have the same probability, leading to this Dilbert comic that is included in, I think, all cryptography textbooks. OK, cool. So randomness is a little trickier than it seems sometimes. And I want to say that there are actual random number generators out there, sort of in theory, like quantum mechanics or at least that's the accepted wisdom right now, that quantum mechanics produces true randomness. And let's say I like toss a ball and it's kind of windy. It might end up anywhere, really. But now let's say I have like 5,000 instruments to detect the wind. Suddenly it's not as random because I can predict what the wind might do to it. So it kind of depends what information you have and what you can measure. Like thermal noise on your computer is only random because outside things can't measure it. OK, cool. Those are actual random number generators. We're not really going to do that. We're going to talk about pseudo-random number generators, which the idea behind a pseudo-random number generator is you choose properties. This is going to get even more fun to say when I add this to it. But you choose properties that you want about random number generators. Like I want it to be uniformly distributed, or I want it to be unpredictable, or things like that. And you try and make some algorithm that will do that. There's actually these things called the die-hard tests, which is just an amazing name for a suite of tests that test sort of how random something is, statistically speaking. And I also want to mention that a pseudo-random number generator in general is actually less than what we might call a cryptographically secure pseudo-random number generator. Spring, as it's pronounced. OK. So but before we get into cryptographic security, let's just talk about pseudo-random number generators in general. They often involve, or they actually always involve a seed. So you come up with some seed value, and that's what you use to start the random number generator. And then you go from there producing random numbers from the previous values, et cetera. And there's something called the middle squares method, which I encourage you to look at. It's kind of a very simple example of something that's it's not a great random number generator, but it's pretty decent considering how simple it is. And there's also something called the Mersenne twister, which is more complicated, and it's harder to see why it generates better random output. But it's still one of the simpler random number generators out there, and it's a little easier to grok, but much more advanced than the middle squares method, which is not great. All right. So cryptographically secure pseudo-random number generators. That is quite the acronym. So these are just as good as pseudo-random number generators with two more things. The so-called next bit test and state compromise extensions. You don't need to worry about the details here. Essentially, it means that you can't take any number that ever got generated by it and figure out any other number that ever got generated by it, which is kind of a very hard thing to do. And unfortunately, also not something we're going to talk too much about. So, because we're going to try and use today to cover things more like hashing and encryption, really, in our workshop time. But I want you to know about these things. Any questions so far about randomness or anything else? Or from our remote audience, if we have one? I think we have one. OK. OK. Hashing algorithms. So that was randomness. Now I want to talk to you about hashing algorithms. But I actually want you to talk to me about hashing algorithms. What are they?
A way of indexing things.
A way of indexing things. Keep going. Say more.
Using an algorithm that will, you'll get the same thing. If you put the same thing in, you'll always get the same thing out.
Yeah, OK, good. So a hashing algorithm, it always produces the same output for a given input. What does it make that function, by the way? Pure function. Great, cool. This is just random functional programming stuff. But excellent, it's a pure function. So how about, let's see. So all we know about hashing algorithm right now is that it produces the same output given some input. So what about if I were to just take two, here's my hashing algorithm. I take two strings and I just concatenate them. Is that a hashing algorithm? It's pure though, right? It always produces the same thing. OK, so what's another property of hashing algorithms then? If you know about it. Yeah, please.
They're taking every character of this input and transforming it into the, it's representing number value.
Oh, yeah. So a common, yeah, exactly. A common way to do this is to take, yeah, exactly, to take every character in the string and get a number out of it. But that's not actually something I would say you need to do. Like, that doesn't actually define a hashing algorithm, but it is very common practice with one. Anybody add anything else?
It's supposed to be unrecognizable from the original input.
Unrecognizable from the original input. OK, great. So, so like, let's say we have these two strings that we want to pass into this hashing algorithm. The output, we should not be able to figure out the two strings from it, right? OK, cool. I'm going to add actually a couple additional properties to that. So this converts a string to another string. That's a hashing algorithm. We call the input string the message and the output string the digest. And the idea is that the message always produces the same digest, and the digest is always a fixed size, which is an important concept here. So like the digest is always going to be 64 characters. If you put the message as all of the text of William Shakespeare through this thing, it will always come out with 64 characters. If you put the letter A through this thing, it will give you 64 characters out. And usually we think of this as a compression, because usually you're passing something larger into a hashing algorithm and getting out something much smaller, which is a key reason we sometimes use it in hash tables, which is, I think, what you were mentioning earlier, usage in hash tables. So there's one other really, really important thing about hashing algorithm. It is irreversible. And I don't just mean it's hard to reverse. I mean it is impossible to reverse. You cannot reverse it. Can anybody think of an irreversible algorithm that you know? You've probably known it since you were 5. Maybe since you were 4, maybe since you were 8. I guess it depends on your education. Yeah?
Summing two numbers?
Yes, addition. Okay, cool. Addition, if we take two numbers, 5 and 6, we add them, we get 11. So now let's try and reverse this, because we don't know what the two inputs originally were, let's say. So we have 11, and I ask you what were the two inputs. You have no idea, right? It's not that it's hard to reverse. It's impossible. There are too many possibilities. It could be kind of any number of things. So addition is a kind of irreversible algorithm. It's not a particularly good hashing algorithm, just so you know, but it is an example of this irreversibility. I also usually, in fact, every other time I've run this workshop, when I've asked that question, somebody has said Pig Latin. But I want to ask you all, why is Pig Latin not a hashing algorithm?
You get a different quantity of output or length of output.
That's absolutely true. Yeah, though why is it not irreversible, so to speak?
Yeah, because you can tell what word it originally was.
Yes, if Pig Latin was a hashing algorithm, there would be no way to understand somebody because they would say something in Pig Latin and you'd have no idea of knowing what they actually said. There would be no way of reversing it back to English. Okay, so some other really good hashing algorithms out there, SHA-1 and MD5. Your neurons are kind of hashing algorithms too. They take a lot of inputs and give out one output. I wouldn't suggest using them for hashing algorithms in general, but it's an interesting example. But if you are curious to read more, like the really SHA and MD, those two hashing algorithms are really big ones out there, if you're curious to read more about these. OK, so we've talked about what hashing is. So why do we have it? What's the possible use case for this kind of thing? Apparently, it is not Pig Latin. Please.
In encryption, you could verify that the message is the correct message when you decode it. Like
Okay,
if
cool.
you send a hash at the end, someone can verify that the message is the hash.
Yeah, great. So verification of something. Yeah, so like if I send you a piece of software to download, and I also list out the hash of the binary or something in the download page, you can download it, and then you could hash it yourself with that same algorithm, and you could look, and you could visually just compare the two outputs and see, did I download what this person said they're trying to send me? And if not, along the way, maybe somebody injected something weird into the binary I just downloaded. So absolutely, if we want to confirm that the message came across as intended, we can do that. Other reasons? Not even necessarily just cryptography. We've hinted at one. Please, yeah.
Building a hash table for data storage and lookup?
Yeah, we use these for hash tables. So I'm going to add a bunch up here right now. So we might classify these, we might because I did, and so now you are going to, as like identity and cryptography. So hashing algorithms are useful outside of cryptography just for things like hash tables. There's a thing called a Bloom filter, which is actually pretty similar. You've seen hashes as git commit IDs, if you've ever noticed that. That's a hash of all the files in that Git repo right now. So it's useful for identifying things without trying to check literally everything in them. Like you could check for equality without, if you have two hashes, you can check whether those came from the same value without having to check literally every bit of the actual input that they started with. In cryptography, we use them actually all over the place. We're going to talk about password verification in a second. As well as in verifying the integrity of something you downloaded, which is a really good example you brought up. Actually, some pseudorandom number generators use them. Because you can imagine if your hashing algorithm is uniformly distributed, and if it's irreversible, it actually makes for a pretty good cryptographically secure pseudorandom number generator. You basically take your input, send it through your hashing algorithm, your seed value for the random number generator, and then you have a new one. And you know it's impossible to go backwards, because that's exactly what your hashing algorithm does. It should be impossible to go backwards. I also want to say There are some funny use cases for hashing algorithms, like proof of work. So in cryptocurrency, like you can essentially say, like, try to find two numbers that will hash to something with 16 zeros at the end of it, or something like that. And that's just hard to do. You're literally giving computers busy work on purpose, because they're basically trying to reverse engineer these hashed outputs, which is a hard task. And in doing so, you have a proof of work that they must have gone through the effort of doing something. So it's kind of an interesting concept of just like effort. So let's talk. OK, so that's why we use hashing algorithms. Any questions about that or what they are? Because we're about to talk about how we might build one. Excellent. So, OK, so here's the idea behind our hashing algorithms. Like, you can kind of think of it as a three-step process. This isn't the only way to make a hashing algorithm, but this is one very, very common construction, or one very, very common pattern. And it's known as the Merkle-Damgard construction. Don't know if I'm pronouncing that right. But the idea is this. You take the input string, you pad it to a certain size, and then you split it up into partitions. And then you take all of those partitions and you do this. You just like squish them together. So like let's say we started with all the text of William Shakespeare. We're going to take that and pad it. And let's say we want a hashing algorithm to produce something that's 64 bytes at the end. We're going to take that and pad it so that it's divisible by 64. Then we're going to take 64 sized chunks until we get through all of the text of William Shakespeare. And then we're going to take all of those 64 byte chunks, line them up like this, and combine them all into one single 64 byte chunk. Does that make sense? Cool. And it makes sense that that would be pretty irreversible too, right? Like we just took everything and smushed it down into a tiny little piece. And now let's talk, so that's a generic how. Now let's talk even a little bit more specifically in the workshop. This is the very specific how that we're going to be pushing you towards. It's this so-called simple hashing algorithm, which is authored by me and not at all cryptographically secure. But it gets across some of these ideas of what goes into a hashing algorithm. So the idea is that you're going to pad the string to at least twice the desired length that you want for your hash digest output. You're then going to partition it into chunks of that desired length. And then you're going to combine these partitions. We're going to do so using XOR. Who's heard of XOR before? Just raise your hand if you have. Cool. It's good that not everybody, because we have an aside here. So how about AND? Who's heard of AND? OK, great. Yeah, AND is a little more famous. So here's an XOR and AND are both what are known as bitwise or even Boolean operators, where you can imagine they take two inputs and they produce just one output here. What's AND 0, 0? What's AND 0, 1? AND 1, 0? AND 1, 1? OK, cool. So that's the table for AND. We have a similar thing going on for OR, where we have 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 is 1. XOR, does anybody know what this looks like? Yeah, please, come up to the mic, yeah.
It goes 0, 1, 1, 0.
Yes, 0, 1, 1, 0, down that line. Right, so the idea here is that 0, 0 produces 0, 0, 1 produces 1, 1, 0 produces 1, and 1, 1 produces 0. You can imagine that if they're different, it produces a 1. If they're the same, it produces a 0. The other way I like to think about it, this helps me think about it a lot, is you can imagine, here's what I'm going to call the left bit, this thing here, and this is the right bit. You can imagine that the right bit is potentially flipping the left one. So like if the right bit is a 1, it's going to flip the left bit. So let's look at 0, 0. Well, that's a 0 on the right, so it doesn't flip 0. So we stick with 0. This is a 0 with a 1 on the right, so it does flip the 0 to 1. This is a 1 with a 0 that doesn't get flipped. This is a 1 with a 1. So there's a 1 here, and it flips it to 0. I'll return to maybe why that's a useful way of thinking about it. But I want to ask you, why would we? So I just said that we're going to be using XOR in our simple hash. So why aren't we using and or? Notice anything about XOR that's useful? Yeah, please come up to the mic as well.
I mean, it seems like it would be potentially more difficult to like reverse engineer from the result, but now I don't know if that's right. So I think I might just be, I haven't had coffee yet.
Okay, that's totally fair. Any other thoughts? Just look at the rightmost column of the output too. Yeah.
Yeah, you don't you don't know your starting point based on, because if you go to 0, you don't know if it was both 1s or both 0s.
That's true. Actually, yeah, that's an interesting point. That to some extent, if you have a 0 here, you don't know which one it came from or something. Whereas if you have a 0 here, it must have been 0, 0. That's definitely true. That's probably a good point. There's something else I'm going for as well.
The 0s and 1s are uniformly distributed?
Yeah, we have an even distribution here. So remember that for our hashing algorithm, we want to produce like a uniform distribution of all the possible 64-byte characters or something. We don't want to always produce the same kind of stuff. And one way we can ensure that is by making sure we have an even distribution in our method that combines things. So we don't end up with, like if we were using AND, we would end up with probably just a ton of 0s in the output. And with OR, we'd end up with a bunch of 1s. And in fact, with a large enough output, we would kind of always end up with only 0s for AND and only 1 for ORs. Because they would just keep combining and filter out those 0s and 1s, respectively. So here we have an even distribution, which is good. OK, so now I want to talk about cryptographic hashing. But before I do, I want to have a small metaphor, which comes from one of the classics of our time, SpongeBob. So in SpongeBob, if you haven't seen it, there's a character called Plankton who wants to steal the secret Krabby Patty formula, which must be very valuable. So, and you can think of cooking as a kind of hashing algorithm, right? Because you take a bunch of ingredients and you put them together, and now like it's hard to know what ingredients went into it. So like one of the things Plankton does is, right, he tries to steal a Krabby Patty formula and taste it and figure out what went into it. But of course, that's not technically possible. Like you can guess, but you can't know that you're right. And so I want to talk about cryptographic hashing now, because cryptographic hashing is more about thwarting Plankton, making sure that if you actually hash something, it can't be easily guessed or it can't be easily reproduced somehow or anything like that. So it's the same as ordinary hashing algorithms, but with these three things going on. Let's start with collision resistance. Does anybody know what this is? It's often talked about out there with the birthday paradox. Are you having fun tracking me too early? And I keep roaming a lot. OK. OK, great. That sounds easier. Yeah. Great, yeah. It's to make sure no two things ever end up in the same spot. So the idea behind collision resistance is we want to make sure that it's not likely for us, given the hashing algorithm, to produce two inputs that happen to collide. Because then, if we can do that, we might be able to guess something about like if we can do that, we might be able to give a program an input, and it would hash it, and then we would actually have another sort of secret backdoor this, which is our other input that we already know collides with it. So it can be useful in some cases. But pre-image resistance is actually more interesting here to me, especially when we start talking about, you know what, we should get more to use cases of cryptographic hashing, and then come back to this. So let's do that. Here's something called HMAC. And the idea behind an HMAC is actually not that hard once you got the idea of what hashing is. You just take a key, add it to the message beforehand, send it through that same hashing algorithm to get your digest. So this key is a secret. And the idea is that you could use this to, if you have a key and somebody else has a key, you could tell them that you've received a message by hashing the message plus the key. Then you send over the digest. If they have that same key and that same message, they can confirm that not only did you receive it as they intended to send it to you, but also that you actually received it, right? Because you were the only two people that have that key. Or there's a similar idea, but you could do that for yourself in the future, kind of thing. Like if I take some diary entry I've got and some key, some secret that only I know, I could hash the key and the diary entry right now, and in a year I could come back to that message, that diary entry I wrote, and hash it with that key. And what I would see is, has anybody altered this message? And did I indeed actually write this? Because if I didn't, I wouldn't see the right hash there. OK, cool. So this seems a little strange, but you can imagine it's actually kind of useful for read receipts on the internet. So this is a cool example of where we can use a hashing algorithm. And it's very simple. It's really just a hashing algorithm where we just add a key to the incoming message. And now I want to talk about this thing. This thing is called PBKDF2, password-based key derivation function, and it's the sequel, because the original was just such a hit. So, so we have the idea behind PBKDF2. You take a password, you take some salt, you add it to the password, and then you hash it. What does that sound like? Which we kind of just talked about. Huh? Cookies?
Cooking.
Oh, cooking. It does sound a lot like cooking. Yeah. Yeah, it is. There are some things we could talk about there. Salt and hash and yeah. But the idea is that this user's password is coming in. And what we're going to do with it is take their password plus some secret that only we know and hash them together. So what is that step like? Or what is that step in a way? We really, here, huh? An HMAC, yeah, exactly. So this is an HMAC. Inside of PBKDF2, we have this HMAC where we take the user's password, that's the message. We take our salt, that's the secret, smush them together, hash them, we get something out. And then we do that like 10,000 times, over and over and over and over and over again. And then we get out this hashed output from our original user's input password. Anybody have a question? Yeah, why on earth would we do this? OK, so I'm actually going to ask that right back to you.
Are you putting in like the output of the first like and hashing it?
Yeah, hashing, yes, exactly. We're hashing it over and over and over again. So there are a lot of questions we might ask here as to what the hell is going on here. Like, why would we hash passwords at all? Why would we salt hash passwords? Why would we repeatedly hash over and over and over again? And another answer to why, we're going to get into the technical answer, but a pretty compelling answer is to avoid a $5 million lawsuit that I think LinkedIn faced, and I don't remember the outcome of it. But you can, here's the link to that. So that's a compelling social reason. But what about what's the problem if we don't, technically? Tell me about user passwords. What's different about user passwords than, say, like their profile information? Like their email, their favorite color. I don't think this is a trick question. Might be, but yeah, please.
People reuse them?
People reuse.
Like their own passwords across many
Oh,
services?
that's true. People reuse them. Well, people reuse their profile information. Like if 10 different things ask for my favorite color, I'm probably going to give them the same answer.
You want your password to be secret.
Yes, secret. OK, good. So we want it so that users' passwords are secret. So now let's talk about, let's say we didn't do any of this. Let's say we didn't hash passwords, we didn't salt passwords, we didn't repeatedly hash. There was none of this going on. So here's what it would look like. We would, and this is actually what author looks like right now, just so you know. So we would get a user password. They would submit it through a form to our backend. It would head over to our backend. Like it would say, my password is I love cats or something. We would just store that in the database right here. Username, Bob, password, I love cats. So what's the problem with that? Yes, please, come on up. Yeah.
I mean, if somebody gets into the database, like it would, like they can just get the password, or if anybody can get access to it, you don't have any sort of more secure store.
Right. If anybody ever gets access to the database, you're done, right? You just, all of your users' passwords are now compromised. So, okay, so why would hashing passwords help that? Please.
You would need to, in order to get people's passwords, you would need to get into the database and then also get the hashing algorithm that hashed the passwords.
That's true. We would also need the hashing algorithm. But let's say they had it. Let's say they had the hashing algorithm, and they had our database. How would they get the passwords? It's irreversible, right? So even if they have the this is a really important thing about hashing algorithms to just remember, right? They're irreversible. So even if somebody has the hashing algorithm, we don't care. We could actually publish it. We could tell the world, like, we're hashing our passwords on our database with SHA-1. It doesn't matter if we tell people, because the idea is they can't reverse it. They can't go backwards and say, oh, here's this input. I can now reverse engineer, or sorry, here's this hashed output. I can reverse engineer what the original input was. Okay, so we hash it, and that way, so here's what it looks like now. They enter their password, they submit it to us, gets to our backend. Our server says, hash the thing. Okay, cool. It was I love cats. Now it's JADS82. And then we store that in our database as JADS82. And now, if somebody gets access to our database, they don't know what the passwords are. I also want to go tell you about the login step at this point, because I just talked about user creation. I just want to show you that login is still very possible. So if now somebody goes to log in, we already have their hash password on our database. They'll enter in like Bob and I love cats. It'll get sent over. We'll look up their username, Bob. Yes, Bob exists. Then we'll say, OK, Bob exists. What's their hash password? It's JADS82. What's their password attempt? It's I love cats. Hash their password attempt. Oh, look at that. It looks exactly like the same thing we've got in the database. So we can still verify that somebody enters in the correct password. But nobody else can reverse and go backwards from from JADS82 back to I love cats. OK, so if that's the case, if what I just told you is perfect, why are we bothering to salt our hashes? Yeah, please.
Like in your example, I love cats is only 9 characters long, so like people could just take the hashing algorithms and like try every 9 character long password and just see the one that works.
Right, great. So fantastic. So even though our hashing algorithm is technically irreversible, that doesn't mean people can't just try everything, right? People can just try all sorts of inputs and try to guess it, and eventually they'd be right. So if we salt our hashes, though, why does that help? So let's talk about the new situation that I'm proposing. Situation is this. Our user enters I love cats. We send that to our server. The server adds a salt to it that just says foobar blah, blah, blah. Whatever salt we generate, we just add that to the end. So now the whole thing looks like I love cats, foobar blah, 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 or whatever I originally said. And then we hash that, and now it's clogs or something. That's the hashed output. I computed that really fast in my head with SHA-1. I'm really good at this. And then we have that in our database now. So why is that any better, though? So like, OK, so now let's say somebody has clogs. Why is this better? Why can't they guess our password as easily? What? Do they know your secret? Which secret? The blah, blah, blah part? Do they know it? Let's say, right, if they don't know it, it's now pretty impossible, right? Because they would have to guess that. But actually, let's say they do know it. Let's pretend they actually know what salt we added. Because we actually have to store that salt somewhere, right? We need it somewhere. And actually, we probably are just going to put it right next to the hashed password in the database. So now it probably feels like I've just taken away the whole point of it, right? Like, why is this any better? So to talk about why it's better, we're going to talk about rainbows. Rainbow tables, sorry. So, OK, yeah, I know, sorry. So here's what dastardly people came up with a while ago. OK, unhashing passwords is hard, but there are a lot of common passwords out there. So why don't we just pre-compute a bunch of hashed passwords? Like, why don't we just go down and try the password I love cats hashed with SHA-1, hashed with MD5, hashed with et cetera. And so they do this once, and they generate this big table of the most common passwords and the most common hashing algorithms. It has a bunch of entries, but they did it once. Now they're done. They did this once, and now they can go around, and actually you could download a rainbow table from somewhere. You wouldn't have to go do this. But they can go around and find these databases, and if they get access to them, they can actually really, really quickly check if any of those common passwords are in this database. So why does salting help that? Why does salting make that much more difficult? Yeah, please. Anybody? Yes. Yeah.
I guess you can that easily guess what decryption algorithm was used for that specific password.
Yeah, so that's fair that we might not know which hashing algorithm, but let's say they have the 10 most common ones, or the 30 most common ones, and we're using one of them. And let's even pretend our user's password is still I love cats, which is one of the, let's say, the most 10,000 common or something. Yeah, please, if you have a...
Every website's going to have a different salt, so you'd have to like have a rainbow table times however many characters are in the string for every single site.
Right, exactly. As soon as you add the salt to this equation, it's impossible to use these rainbow tables. They're meaningless. And in fact, if we have a particular salt per user and not just per website, suddenly even knowing the salt for a user doesn't help you. You still have to try. So the whole point of a salt is making sure that if somebody's going to guess the password, well, at least they're going to have to try to do it. We're going to have to make them work hard to do it. So one of the ways they're going to have to work hard is they're going to actually have to try all the 10,000 most common passwords again and again, every single time they want to do this, with this particular salt for this particular user in our database. It's a much harder problem than if they had been able to start with all the most common passwords and just look through our database for those hashed results. OK, so now it's harder. Why would we repeatedly hash? So there's something I said about PBKDF2. We take the user's password, we add a salt, we hash it, and then we do that like 10,000 times. Yeah, please.
In addition to trying to guess all the salt, you now need to guess how many times it was repeated, the hash was repeated.
Oh, cool. Let's say they know it was repeated 10,000 times.
Oh.
But yeah, great. Good, right? So maybe it adds another secret level, like they need to know the number. But now let's say they know it. Because like, let's say they have access to our source code, because they used to be a developer for us or something. So also think about the difference between if I told you to do something once versus if I told you to do it 10,000 times. Yeah.
It just literally takes forever.
Yeah, we're literally slowing things down.
Yeah.
So this is really fun. This is one of the only times in computer science where we're trying to slow our algorithm down on purpose. It's not an accident. It's absolutely on purpose. So repeating it over and over again makes it tunably slow. So we can say, I want to do a PBKDF2 and repeat it 100,000 times, and it's going to take 500 milliseconds. By the way, when I'm talking about slow versus fast here, I mean slow for a computer. Like, doing this repeatedly 10,000 times is still going to be like milliseconds, which to us, we can't distinguish that from a nanosecond. Like, but to a computer, it's like so much slower, right? And if somebody has this database of hashed passwords, and they're going through and trying to guess them, it's going to take them 10,000 times longer than it would have if we didn't repeat each hash 10,000 times. Yeah.
Right now, there is like also opinion about it. Like people are developing the quantum computers, so this would
Sure.
be not that slow.
Well,
if
this
you
would
would use
actually, yeah, that's a good question. So as far as I know, quantum computers are not faster at hashing algorithms. And they can't parallelize hashing in your database. Quantum computers are faster at prime number factorization, something we might talk about when we get to encryption. But I also want to say that, just a teaser, quantum computers also have their own cryptography, new cryptography that they bring to the scene. So what they take away, they actually give as well. We might get to talking about quantum computers at the end. It usually devolves into that. So I'm glad you brought it up. OK, any questions about that stuff? I have a question, you have a question, and yes, I can hear you.
OK, so if part of the problem is if you're on a database as a DBA and you have access to passwords, there's legal culpability. If someone has access to the server, couldn't you hijack into where you're actually running the hashing algorithm and just a line before store that information somewhere else? Like if you don't encrypt it before you send it out from the client, isn't there still a giant gaping hole in security?
Yes, so if somebody has access to the running server itself, then yeah, you're kind of hosed. Though I think that's a problem anyways. So one good practice to avoid that is you could take the password that the client enters on the client side, salt and hash it there, send that thing across, salt and hash it again, and then store it. So that would mean that even if somebody had access to your running server, the only thing they would ever see is the salted hashed version of it. But if they have access to your running server, you'll probably have a lot of problems. You know what I mean? But it's a good point. OK. Yeah, and I think LinkedIn was not doing this, and people got upset. That's what that link is referring to there. OK. So now let's talk about the workshop. So we're going to have like 2 phases today. We're going to be doing the first 2 parts of the workshop, part 1 and part 2, in the morning. And we're going to be doing parts 3 and parts 4 in the afternoon. Parts 1 and 2, which is what you all are going to be doing now, is generating a random string, generating a simple, but again, really, really bad hashing algorithm. But it does get across the idea of what goes into a hashing algorithm. And then using that to make HMAC and to make PBKDF2. So you're all going to be doing these 4 things. Any questions before we get started? Well, that's too bad. OK. OK, so I'm not answering any of your questions, even though you all have so many of them. By the way, we'll get to encryption after this. So I'm going to be opening up the workshop now. Feel free to work solo or in a pair as you wish. And if you're at all curious about working with any of our remote students, you can try to reach out to me. And they might reach out to me too and see if they're interested in working with you. So cool. Have at it. You can go find your working station for today, and I'll be sending out links soon in your Slack channels. It's true, yeah. Senior area is yours.
So encryption is the one that deals with prime numbers.
Yes. There might be some hashing algorithms that deal with prime numbers. I don't remember. I'm sure there are. So, Elliot, are we out there?
Give me the 10-second loop.
Huh?
Just give me a few seconds.
Oh, okay, cool.
Yeah, you're good.
Okay, cool. So I'd like to start this off by just listing up any questions ahead of time in this little notes file. So what questions do you have? Including remote people. There might be no questions, is what I'm gathering. But I'm going to give the remote people, they have sort of the moon landing delay kind of thing, because the broadcast takes some time to get there. So I think there are probably no questions then. Yeah.
Sean in remote asks, is there any reason we would change the base set of characters from base 64 to something else?
Any reason to change the base set of characters? Yeah, actually I'm going to add another thing to this, which is what's with the base 64 strings in general. Cool. Which I think will probably answer that as well. Okay, so I just want to say, all this base 64 string stuff, this was just to have human readable output. So that like, if you have this stuff, you could console log it and like slice it and it wouldn't look weird. Because there's a lot of Unicode that is just going to look like crazy question marks and emojis and things. Like it'll just not log well. So the whole point of any of the workshop bothering to convert to base 64 strings was just for human readable output. So as far as the base set of characters, you might change it for compliance. Like I haven't actually checked whether the base 64 we're using here is the base 64 that people use in general. So that's a pretty good reason. All right, those are all our questions. Okay, let's do it. Let's start with random, and we'll start walking through what we want to build. So somebody tell me about random integer. What does it take and what does it return? Sorry, instead of telling me, tell Mike. Yeah.
So it takes minimum and maximum,
Okay.
and it returns like random number in between this minimum number and maximum number.
Got it. So somewhere in between there. Okay, cool. So I think the magnitude of this, so if we have 5, 15, the magnitude is 10, I think. So we should be able to do something like max minus min and multiply that by our existing math random to basically get a value between now 0 and 10. And then we should be able to add the minimum to that to get what we need. Except what? Huh? Yeah, we should round it. So let's, in fact, let's, instead of rounding, I'm actually going to math.floor. If we round it, here, let's call this in range. And we'll math.floor it. So if we round, we're actually going to get the smallest and largest aren't going to be as likely as any of the middle numbers, if that makes sense. Because we'll get like, if we get 0.49, that'll go down to 0, but 0.5 will go up to 1. So the range of 0.5 to 1.5 will go to 1, but only the range of 0.49 and down will go to 0. Same with the upper range. So we should math.floor it, but this will lead to another problem. Anybody know what I'm talking about? Let's run it. Let's go put in this test spec, exit, like that. Okay, So if we look at this coming from line 33, we see it expects us to generate, where were we? Right, it expects that if math random is returning basically 1, that random integer 0, 10 should return 10. So this is inclusive and not exclusive. So we need to add 1 somewhere in here. I think it's here. I don't know. Let's try it and see what happens. It worked. I'm going to assume that was right. I'm going to assume that was OK. And it makes sense. We need to increase the magnitude of the number we might be generating by 1. Cool. Let's get it to default to 0, which is kind of a pain. Like we can't, so in ES6 we can do this to get a default parameter. But this will only work if we do something like random.integer and we invoke it with undefined and 10 or something like that. Then we'll get this to default to 0. But getting this to work is a little bit awkward because this is going to think we're setting min to 10 and max is going to be undefined. So here's potentially a neat trick for that. We can call random integer again. So let's say if the argument's length is less than 2, we're going to call random integer again with 0, comma, and this first argument here, we can call it arguments 0, is now going to be the actual maximum that we call it with. Let's just add a return statement there and we should be good. Instead of argument 0, though, I can just call this thing min. So I will, because it's named. So I think probably there were some questions people had about how can we get a default value for a parameter towards the front of a function, and there's not like a great way, but this is okay. Any questions looking at this? All right, tell me about random base 64. What does this take and what does it return? Yeah, it takes the size, the length, let's call it, is a good name for it. The length of the string we want to generate. And then it uses this character set. So what we're going to do, we're going to add to some random string here for the length. So now we're going to get 64 random characters if the length says it's 64. Because each time we're going to do rand string plus equals and get a single character here. Then at the end we can return that. OK, so now what we can do is use our own random.integer here to get something between 0 and 63. And we can index into this base 64 character set to get something from it randomly. Let's see if that does the trick. Let's try it out. Describe random. OK, that does the trick, which is good, but a little boring. I was hoping it might break. Any questions looking at the random stuff? Did anybody bother doing the middle squares method? Do you want to see that? Ringing enthusiasm. Yeah, let's do it. OK, so here's the idea behind middle square. So it's going to take some seed value. Let me actually open up this link, which is really just Wikipedia, I think. But I really like the Wikipedia link on this. Middle squares. OK. So the idea behind the middle square method is like start with the seed, square it, so just multiply it by itself, get this number, and then take the middle part of that and use that as your output as well as the next seed for the next time around. So I'm going to make a sort of middle square generator. The idea is that this will return a function that we can use. So like it would be something like random.middlesquare generator. We invoke that on 675.248, 675.248. That comes back with our middle square RNG. unmarried, as we can see here. And if we call it, we want it to come up with 959,861 the first time. If we call it again, we want it to come up with whatever the next value should be, etc. Okay, so what we can do in here is we can take the seed and multiply it by itself. That gets us the square of it. And let's go ahead and toString that, because we're actually going to be like trying to chop it up like it were a string. So let's call this the next string. And getting the middle of it's kind of awkward. We basically want to do something like the next string length minus the seed length divided by 2. And that's going to get us like our starting point. So if we take the difference in length between this very large one and this one, and then divide that by 2, we should be able to get 3, saying like start at the third character. So hopefully my math is right there. And let's call this sort of like the start. Okay, and now that we have the start, we can take next string and we can substring it from start for seed to string length. And that's going to be our next seed, and we return it. I'm hoping. I'm noticing we're doing this seed to string length a couple times. I'm actually going to just cap that once as seed to string length. Okay, so this is going to be the size of the number we generate, and we'll just use this anytime we need it. So this is kind of fun. Let's console log this and see if it gives us what Wikipedia says it should give us. Maybe not. Next string is not defined. Oh. T.
And
There's another one. So I clearly should get a linter, by the way. It's one thing that will become very obvious to you all throughout the course of this review. There it is, 504. That does not seem right. Is it I hope not. There's no server. Do I need what?
Parentheses.
Oh, yes. Order of operations. Thank you. That will definitely make a difference. 959,861. Yes. Okay, cool. So this is kind of neat. And you can imagine why this works good as works okay as a random number generator. Because when you just square a number and take the middle digits, it's not like they're correlated at all to the original. And it should get you a nice random distribution. So this is a cool build your own random number generator that we just made. And it's like 6 lines of code. That's kind of fun. Let's go into hashing now, though. I'll comment this out. So hashing stuff. Tell me about, let's run through these in order and just start speccing them out. Pad, what does it take and what does it return?
Characters that you want to pad the string with.
Okay, cool. So like the desired length or
Length,
something.
yeah.
Great. Excellent. How about, and what does it return?
Oh, and then it returns the string padded with length characters.
Cool. It returns the string padded with length characters. Great. And I'll just call that thing padded for now. How about partition? Somebody else. What does that take? What does it return?
It also takes a string and a length,
Okay.
and it returns an array.
Okay. It returns an array. So I'll call that thing partitions and return it. Okay, how about combine? What does that take in return? Somebody else.
It takes 2 strings.
Cool. This one takes, call it string A and string B. Okay, cool. And what does it return?
It's going to return the base 64ified version of those 2 strings combined, so a single string.
It returns, cool, a single string, base 64, and XORed,
Yes.
I think. Okay, great. So return XORed string. Okay, cool. And then finally run. What does run take? Somebody new. I know it'll be like, we'll probably run through everybody pretty quickly with that, but please.
It takes the message or string and a length, and it returns the hash that is the proper length.
Yeah, great, cool. So this is like the actual hashing thing here, this hash simple run thing. This is the actual hashing algorithm. And it will, well, I'll call this thing a digest. And it's going to do so by running the previous ones above it. So let's start filling these in. And by the way, some of the choices here are very particular to this hashing algorithm. So I definitely want to get across the general concept that we might build a hashing algorithm this way. But some of the specific choices are not that important. Like the way we're about to pad this is a little bit arbitrary. Like we're going to take the string, and we're going to get the reverse of it. So we could go down for I in every character in the string. We will, let's do this the other way around. String length minus 1 while I is greater than 0. I minus minus. Okay, cool. And let's do reverse plus equals string I. So this is just to give us something to pad onto the end of it. And then let's do something like while the padded is less than, well, the padded length is less than the length. You know what? Let's start the padded out as the string. And then let's keep adding. The idea is we can keep adding the reverse of itself to the end of it until it's at least as long as we need it to be. That's the idea behind this particular padding scheme. Okay, let's try it out. Anybody have any questions about why or anything like that? Parameter name not allowed. Oh, I double named. My bad. Am I? Oops. Yep, thank you. Also, okay, so that's pad. But so let's run it and see if there are other infinite loops that I missed or anything like that. It seems to be doing the thing we want it to. So any questions about why we're doing this or anything like that? Why we're not doing it a different way? I don't know. Anything. Cool. Okay, so let's go on to partition. So partition, we just need to go down the string and get certain chunks of it. So I'm thinking, what am I thinking? You probably don't know what I'm thinking. So let's do this. Let's do a for loop. We'll start our index at 0. We'll go as long as it's less than the string's length. And we will, actually let's do it this way. Let's increment I by the desired length each step. And then what we can do is push to this partitions a substring starting at I for the length. So we'll basically say like start 0 to 5 and then go 5 to 10 and then go 10 to 15, etc. Hopefully by the end we have all our partitions.
Hey, Omri.
Hey.
Sean is asking why are we padding with the inverse minimum once?
The inverse minimum once. Inverse minimum. Oh, wait. I think that comes in a little later in run. Like we're padding at least to double the length. Is that the question? I'm going to give it 20 seconds to see if that settles. Okay, great. So we'll get to that soon. It's a great question. Excellent. So let's go on to combine. So combine, we have two strings and we want to XOR them. And XOR is not an operation we can do on strings. Actually, I'm curious what happens. Did anybody try it out? Let's just try foo, foo, XOR bar. We get 0. Oh, that's weird. I sort of was expecting like not a number, I suppose, but yeah, 0, okay. So what we can do instead, though, is we actually have a utility function over here for converting, actually here, I think. Well, a combination of places. But we can take a base 64 string and convert it into like digits, as it were. So that each character in the base 64 string is now, it's now an array of like 0, comma 63, comma 10, comma 2. And then we can map down each of those and XOR those things. So if we did an XOR of 7 and 100 or 8, that should give us something we need. All right, so let's do that. Let's go to our combine. Here's our XORed string. You know, I don't think that's terribly important. Should we assume these are base 64 strings? Sure. So now let's do something like base 64 2 digits on string A and string B, giving us something like digits A and digits B. Cool. And then what we can do is loop down these things and XOR them. So for, you know what, why don't we map? This will be better. XORed digits, digits A, digit A? Yeah, sure, that works. And now we can XOR digit A with digits B. Perfect. And then we just need to convert it back into a string. So XORed string is base 64 from digits, XORed digits. And this will work perfectly, right? No. I think it'll work perfectly. It'll definitely work perfectly. Yeah, it's going to be fine. Okay, let's try it out. If it does that, well, I'll actually be very surprised if somehow this works. Okay, good. This totally does not work. And because we're not really doing the right thing here. If we look back at it, I'm trying to XOR a digit with an array. Okay. So how can I get a single digit from this thing, though? Yeah, please.
You can use the, in map, you can use the index.
Great.
And just getting out by that index from that array.
Yeah. Here, I'll make it a little more explicit. I don't know if it matters terribly, but we can use the index of whatever we're mapping down at the current time to get the corresponding index in a different array, and then we can XOR those things. And this will get us pretty far. I think this won't get us quite all the way. So there's still one thing going wrong, which is if either string is smaller, we want it to go with the longer one, as it were, and just pad by 0 with other numbers. So I'm actually going to do this. I think we don't actually need to pad if we don't want to. We just need to make sure we loop down the longer one. Let's do shorter. Okay. I don't want to call this digit A anymore. I think I'm going to call this a digit, a digit, and I'm going to call this other digit. Okay. So now we just need these longer and shorter things. I think this will work out as long as the longer one is actually longer, because I think if we XOR with undefined, so like if we capture shorter and we get an index that it doesn't have, we should get undefined. And then I believe if we do like 7 XOR undefined, we're just going to get 7. Yeah. So this should be fine. It should give us just the value of the remaining digits for the longer one. All right, so now we just need to figure out which one's longer. So that should be something like digits A length is greater than digits B length. Go with digits A, otherwise go with digits B. And similarly, shorter, we can actually base that off of longer. We can say if digits A is longer, then it must be digits B that's shorter. digits A is longer, digits, yeah, I think so. I don't know. We're going to try it. Okay, and it worked. Neat. So that's our combine. And again, this is another place. This partition is actually pretty generic, but the pad is kind of very specific to our hashing algorithm. Same with the combine. Like we could come up with other combining functions here. So now let's talk about run. It's just smashing all these things together. So we can say, let's get our padded string by calling hash simple pad on string, and then I'm going to do length times 2. We'll talk about that in a second. And then we're going to take the padded thing and partition it. So hash simple partition padded length. Then we're going to take the partitions and combine them. So we're basically going to try and call hash simple combine on the partitions. And we want that to come back with our digest. Cool. So I'm going to ask that question right back to you all. Why do we want to double the length when we bother to pad it? So like the string comes in as ABC. Why are we always making sure that when we go to pad it, it's at least twice as long as the desired length? I should have said that differently. Let's say we have ABCD, and the desired length is 6 or something. Yeah, please.
We always want to have 2 partitions at least.
Yeah, exactly. So this is to make sure that if they happen to be the same size, that we at least have 2 partitions. Because otherwise, we're going to end up doing an XOR and with nothing. We'll just get the original string back from the hash. So the hash should always produce a different string. It should never produce the original string. So if we just make sure it's twice as long as the desired length before partitioning it, we should be fine. It should at least go through one XOR operation. Does that make sense? And I'm going to also ask Sean, does that make sense? And while I ask that question, I'm going to continue. But Sean, let me know. Cool. So there's something wrong with what I've done here, hash simple combine, because it does not take an array. It takes 2 strings. So instead, we could have something like, let the digest be partitions 0. And then we could go through for I is 1 while I is less than partitions length. We could increment I, and we could then get that particular partition, and we could call hash simple combine on our existing digest. Wait. Yes. Our existing digest and partitions I, and then set that equal to our resulting digest. So this is one way that we can now actually loop through all of them and pass it a string and a string as we expect. There is something I believe I forgot up at the top here. I forgot that this string is coming in as a Unicode string. And we're going to do ASCII to base 64 on it, so that we end up with a human readable string if we end up with gobbledygook in our hash. So I'm going to call this thing base 64. And that's the only other place we use it, so we should be good. All right, let's see if this works. If it doesn't, then I'll just give up. Sound like a deal? Yeah, everybody's like, yeah, okay, whatever. Okay, so it totally works. What's a better way we could do this, though? This is a pattern here. Anybody know what I'm talking about? Yeah, reduce, which we should all know a lot about now that we've done Redux, which is based around this reduction pattern, this reducer pattern. So we can actually, this is start with some initial value. Every time you loop, reset that accumulator to be the result of some function, the old accumulator, the next element in the array. That is exactly the reduce pattern. So we should be able to do partitions reduce using hash simple combine. And that should yield our digest. It should just work, but we'll see. Yeah, awesome. So it was like the perfect fit for reduce.
We spent a while trying to get our reduce to work.
Right. So here's something I want to mention. I don't remember if I mentioned this last time we did CS Saturday, but I am cheating 100%. Like I have the answers ahead of time. I've done this like before, right? I'm not hiding that fact. So like if I come up here and I like solve this in a minute, it's because I already know the answer. It's not because I'm figuring it out again right now. So don't feel like if you spend a lot of time on this that's a problem. Just remember that I could be really, really stupid and have memorized exactly what I need to do to get the right answer. So there's nothing you should feel about inferiority here. Yeah, please.
Yes, so on line 47, you're like reducing it and right away passing the function. And it takes the same values. But don't you need to set like the initial value as a string?
Oh, like this?
Yes.
Actually, we don't in this case. Do you know what happens if we don't provide an initial value to reduce? Yeah,
I don't.
I think, so it goes with the, go ahead, yeah, please.
It uses the first index of the array.
Yeah, it uses the first element as that initial value. And then it actually starts the loop or at the second element, so to speak. And it starts running the iterator on the first element and the second element, and that result in the third element, that result in the fourth, etc. So reduce is just like very nice this way. And I mean, when we were making this workshop, we like did this so that it would fit nicely into reduce. It wasn't entirely a coincidence. But to some extent, reduce is nice that way, in that if we've got a combining operation, you can often do things like this, where you just call reduce on that combining operation. Cool. HMAC and PBKDF2, and then lunchtime. So HMAC, tell me about what it takes and what it returns. Name? Wait. I don't get the joke, whatever it is.
I think it takes either 3 or 4 arguments, right?
Yeah, 3 or 4 arguments, great.
The first optional one is the hashing function.
Cool, I'll call this our hashing algorithm, or sure, let's call it hashfn or something.
And then a key,
Okay, cool.
a text, a string,
Okay, cool.
and then a length.
And then a length. Okay, great. And the idea is that we can just take this key plus this text. That's our secret. You know what, I'm going to call this secret. Cool. And I'm actually also going to call this message to fit in with the hashing parlance. And we take that and we call our hash function on it for the desired length. So HMAC is really like not very complicated once you know how once you have a hashing algorithm. HMAC is kind of just use it with a secret, that's all. We do have a very awkward thing going on that we might not be given a hash function, and if so, we're going to default to hash simple run. So we need to do another one of those things where if the argument's length is less than 4, we will return hash HMAC with hash simple run and the rest of the arguments. The remaining arguments here. Yeah, you know what? Let's call dot apply. Sure. The context shouldn't matter, but then we can just pass it arguments. Oh, right. Okay, here's me cheating with spread, but yeah. So we're basically saying apply it with hash simple run as the first argument, and the remaining 4 arguments is everything else. I need the apply because I'm passing in an array here. Yeah, good question. Okay, let's try this out. Let's actually just take this. Well, actually, let's just do both of them at the same time. Let's see if we got any problems. Hashfn is not a function. I'm probably doing something wrong. And we're only getting 1 failing, which makes me think defaults to using our simple hashing algorithm. Hash simple run. 52 arguments. Oh, length? Is that the problem? Okay. It looks like a problem, yeah. Okay, cool. So any questions looking at HMAC? We're about to use it inside PBKDF2. I love this part. Because so PBKDF2 is like a state-of-the-art thing we use for password hashing. And we're going to build it right now. And it's like 4 lines of code. So it's pretty cool. If we understand how it works, we actually understand how some really powerful stuff in encryption works, in cryptography. So this similarly takes a hash function. I think the next argument is the message, followed by the salt, followed by the length, followed by the number of iterations. Followed by the number of iterations, followed by the length. Great. I know we're going to need this. Let's do something like this in a second. Argument's length is less than 1, 2, 3, 4, 5. If it's less than 5, we'll sort of default this somehow. But for now, let's just solve for the more trivial case of if we're given a hash function. So tell me about PBKDF2. Remind me what we do here. A remote student might actually have time to answer at this point.
You HMAC more than once.
Yeah, wow. Okay, great. Call HMAC more than once. And so call HMAC with the hash function, with salt as the secret, message as the text here. I think these are reversed. We'll talk about why, but and length. Okay, so we're going to do this over and over and over again. We're going to do this specifically while iterations, for the number of iterations. Oops. Cool. So let's go ahead and we also want to do this here. Let's have this be called digest. And let's say let digest equal message at the beginning. And then we can say digest equals HMAC over and over and over again. And then we finally return it. So let's see if this does what we want for the simple case. And then let's see if we can get it to the default argument. Yeah, totally. This is PBKDF2. Whenever you go to use PBKDF2, which exists in Node's crypto library, where was I? This is exactly how it will work, except that it doesn't exactly take a function here, I think. I think it takes a string, and you have to give it the name of the hashing algorithm you want to use. But you can give it nothing, and I think it defaults to SHA-256 or something. Yeah, which is one of the SHA family. So, so this is PBKDF2. It's beautiful, and it's simple, given our hashing algorithm that already exists. So let's go ahead and make sure this still works as well. So let's do hash PBKDF2 with hash simple run as one of the arguments. Oh, you know what? I could do a better job here. ... arguments. Yeah, if I'm going to cheat and use ES6 anyways, I might as well not even use apply. There we go. So you can just say ... arguments, and it'll just unpack them for you, which is kind of neat. Yeah, wait, was there a question? No. Oh, okay. I got so excited for a second. Almost a question. So close. Awesome. Amazing. So, I think the big concepts to get out of parts 1 and 2 are like what randomness means under the hood and why it matters, and also for hashing, the components that go into a hashing algorithm and a couple use cases like HMAC and PBKDF2, which are very useful places where hashing algorithms kind of play in cryptography. Any final questions before we break? I'm going to give it about twice as long an awkward pause as I normally would. Which is pretty long. Please, yeah.
In the initial padding choice, this may just be an arbitrary choice, but I was wondering about just why we added the whole reverse as opposed to kind of just like adding characters of the reverse until it equaled the length.
Adding characters of the reverse.
Like when we first started doing, we were just like iterating through the reverse. That's just arbitrary.
Yeah, that was pretty arbitrary. Yeah. Good question. Anything else from the universe at large, Elliot?
He just said we need Final Jeopardy music.
Okay.
That's all.
Good point. Yeah. So there's one remote?
There's 5 watching.
Oh, okay. I thought you were like, there's the one remote person. Okay. Cool. Awesome work. See you back here at, it's actually about 1:45. So why don't I see you back here at 2:45, an hour break for midday, and we'll talk about encryption after that, which is going to be a lot of fun. At least for me, but also hopefully for you.
Can you show your
My PBKDF? Yeah. I'm also going to be pushing this to your library in a sec, so you can look at it there. Welcome back, all. Give me a thumbs up when we're good. Wow, I am carrying. Okay, what's encryption? Yeah, I mean, we're going to answer it over the course of a number of slides here, but... Or if you have a wrong answer, please share that too. That's great.
Like encoding something so that it's only like, readable or accessible with something to decrypt it.
Okay, I love it. Yeah, that works plenty. This is encryption. You have plain text, you've got a key, and you've got ciphertext. And your encryption, with your encryption, you should be able to go from the plain text to the ciphertext with a key, from the ciphertext to the plain text with a key. So it's reversible, which is notably different than hashing, which we just covered. Trying to make this less loud. Okay. And what we're seeing here is the forward step encryption from plain text to ciphertext, and the backward step as well, ciphertext back to plain text. So why do we bother with this? Why not just have a bunch of plain text? Huh? Yeah, please, yeah.
Because that could be read by other people.
Secreting. Yes, being secretive. Great. So we care about this when we're communicating or when we're storing data. We might want to encrypt it so that only somebody with a key can actually access that data somehow. Okay, cool. So that's a very valid use case. And this has, like cryptography has been around for a while now, like since the BCs kind of thing. But it hasn't really mattered that much until recently when we had so much data constantly being communicated and stored. So we've had the same cryptography game going for a while now, but the stakes are just way higher because there are probably like 8 messages being sent just by people in this room right now. So, well, maybe not. There are only 7 of us here. But if we count the remote people, it might work. Okay. Now let's talk about how we encrypt. Language itself is kind of an encryption mechanism. And in fact, in World War II, there was this group called the Code Talkers. So in the Pacific fight, I don't know what to call it, the Pacific area, the US was trying to encrypt their messages so the Japanese couldn't understand them. And they came up with a pretty novel idea, which was to use Navajo speakers. So on one end, you would have a person trying to send a message and somebody who spoke Navajo or the Navajo language. And they would tell the Navajo speaker the message. That person would translate it into the Navajo language, send it over the radio. Over here, you've got somebody who knows the Navajo language who's listening, hears it, and then translates that back into English for somebody else over here. So that's pretty cool. Like language itself can be an encryption scheme, and it was unbroken in the war. Apparently because the Navajo language is so unrelated to any other language. And even just parsing the sounds was very difficult, apparently, for the Japanese, because Navajo contains some sounds and some grammar that's just very, very non-standard, from what I understand. I have no idea. But that's a cool idea. There are also a bunch of sort of more reliable things that we could probably code out, like these things. These algorithms, like the Caesar shift, Vignere cipher, one-time pad. And this is actually roughly in order of history here. So the Caesar shift is actually Roman times. And we're going to talk about it a bit in a sec. Vignere cipher was kind of the Caesar shift taken to a much greater extent, and that was around 17 or 1800s. One-time pad, another thing we're going to talk about. These two you're going to implement, Caesar shift and one-time pad. That's pretty modern. And DES and AES are very modern. I think the last 20 years, maybe even the last 10 years, I can't recall. There are a bunch of others. But this is how we can encrypt stuff. And now let's talk in particular about Caesar shift. Who's heard of the Caesar shift cipher, by the way? Cool. Yeah, it's a pretty common one out there. I feel like you'll find it on the back of cereal boxes as well. The idea here is that you take your plain text and you decide, I'm going to shift everything by 1 character. And so what you do is if it says hello, you would instead say A, B, C, D, E, F. I've got this one. G, H, I, F, M, M, P, something like that. So you shift everything one down. Then to decrypt, you just shift it one back. And by the way, Z and A like wrap around. So if you were to shift, if you had a Z in your message, it would become A. And decrypting, A would become Z. So what's the key here? Literally the encryption key, I mean. Huh? The amount you're shifting by, yes. The amount you're shifting by is the key. Okay. So also, why is this not great in cryptographic sense? Why is it easy to decrypt, though? Just guess the number. Okay, there are probably only 26 keys. But okay, now let's pretend we make the shift. We do like some sort of shift and rotate thing. So it would be like if we got to 27, we would actually like swap A and B, and then we would do the shift. And if we got to 52 or something, we would swap A and C, etc. So now we've increased the possible number of keys we've got by like making some weird way that we can convert these alphabets. Why is it still not great?
You're doing the same shift for every character?
Yeah, we're doing the exact same shift for every character. Great. But why is that a problem? Like, think like an evil genius, and what would you do
You only
about
have to
that?
figure out one shift to break it.
Right, you only have to figure out one shift to break it. And actually, it's probably not going to be that bad because E is going to show up a lot more frequently. So you can do a frequency analysis on it and see what letter appears a lot. And if like there are a lot of K's in it, you're like, that probably corresponds to E. And then you start filling it out. So Caesar shift and a sort of any of these ciphers where you just always replace one character with some corresponding character don't work super well. So let's talk about the one-time pad. I love this one. Here's how you do it. And I'll tell you about the fun magic trick that happens when you do. You generate a key of the exact same length as your message. So if your message is hello, you generate a 5 length key. I know, right? Incredible. So you generate a 5 length key. You take your message, you take the 5 length key, you XOR them, and you send that across. And then you never ever use that key again. That's why it's called the one-time pad. So how would you break this? Any thoughts? Let's also talk about how you would decrypt it. I just talked to you about how we would encrypt it. How would we decrypt?
Some sort of like corresponding bitwise operation on, like, I don't know, it would be like XAND or something on the key and the...
Yeah, so exactly. You take the key, and if you have the key, you take the key and the ciphertext, and you do some bitwise operator to get the plain text back. So I told you something earlier about XOR that I mentioned. You can think of it as a kind of flipping operation. So you can actually use XOR to undo what you just did. Because if you imagine XOR as a flip, then 2 flips, you end up right back where you were. And that's why I bothered describing XOR as a flipping operation, so that we could talk about it here. So that's how you decrypt. And I'm actually going to tell you something interesting about it. It's perfect. You can't break it. And I'm not only saying, like, assuming you don't have the key is where I'm going with this. Like, assuming you don't have the key, you cannot figure out the message. And I'm not even claiming that it's difficult. I'm claiming that you cannot figure out the message. So let's talk a little bit about why. Let's say you go with the brute force approach. You just start guessing keys. So you're just like, okay, I'll guess that the key is A, B, C, D, E, F. That's 5-letter combination. Okay, cool. So you take the ciphertext, you XOR it with A, B, C, D, E, F, you get something. Well, that didn't look like English, so that's probably not the answer, right? So you keep doing that. Let's say you literally go through every combination of 5 letters. That's not that hard. So you do that, and you end up with every possible 5-letter sequence in the English language. Everything. So you just have no idea what the message is. You end up with a bunch of things that are words, a bunch of things that aren't words. You end up with literally every 5-letter sequence in the English language. So there's no way you can figure out which was the original message without additional information. So one-time pad is really cool in that it's perfect cryptography, and it's remarkably simple. Like, you just have to have a key of the same length. You just XOR them, and to encrypt, you XOR to decrypt, which is amazing. Any thoughts for why we don't use this, though? This is not really used, one-time pad.
Couldn't you figure it out from context? Like if you took a full paragraph and broke it into all its content and looked at the words in relation to each other?
Yes, that's if you're using the same key over and over again. Maybe. Oh, a different key per word. But then you would still just get every possible sequence of 4-letter words followed by 3-letter words followed by 4-letter words. So maybe, but in general, you wouldn't. So you might be able to figure out some context if they're sending information piece by piece. Like, especially if somebody sends a 1-letter message, I probably know that it's I or A. I don't know if I'm thinking they're spelling words, right? So there's definitely something we can try to do, maybe to infer. But assuming somebody takes the whole paragraph and sends it in one go, we can't know. There's nothing there for us to parse. We don't even know where the spaces are. So why? Let's pretend it is perfect. Though if you think of like flaws in your head, we should talk about them. But even if it's unflawed, like, why isn't this ideal? Yeah, please.
It's a really simple operation in the middle, and you have to send the key with it in order to get it. So anybody can just intercept it and XOR. Okay, good. So the key. We both need the key, right? That's a very big flaw with it right now. But there are actually plenty of symmetric key cryptography algorithms used out there, and one-time pad isn't really one of them. So notice a couple of things about this. One, we have to generate a key of the same length, and another that we never use that key again. This is expensive. Like, it's good, but it's very, very expensive to do. Literally every message you send, you have to generate a key as long as the message, and then you have to generate another one the next time. And you have to figure out how to share that key over and over and over again when you do this. So even though it's great cryptographically, it's really not particularly feasible. And it turns out, we're not going to be looking at implementing one here, but it turns out there are plenty of other symmetric cryptography systems. And by symmetric, what I mean is just we have the same key to encrypt and decrypt. There are plenty of others out there that are really great. They don't have to be perfect. They're amazing and wonderful and good enough. And much more efficient. So we don't really use one-time pad out there, but it's cool to go over because it's simple and displays some awesome stuff about cryptography. And I really like that you just brought up one of these flaws, because now I want to talk about something else. I want to talk about asymmetric key cryptography. Who's heard of this before, by the way? Does this ring any bells? Sometimes even if you don't know what it is, it's like buzzwords out there. It's also known as like public key cryptography. So here's the idea. There are now 2 keys, key A and key B. You use key A as the encryption key. Plain text goes through that to produce the ciphertext. You use key B as the decryption key. So the ciphertext goes through that to produce the plain text. And you can't do this. You can't do plain text through key A, ciphertext through key A gives you plain text. Key A can't decrypt the message that encrypted. Similarly, key B couldn't decrypt a message that it encrypted. Sounds pretty weird, right? And I guess only about 50 years ago, it was sci-fi. This was not something real. This was something that people were hoping to be able to do. And I'm gonna say a little bit more about how we do it here, which is that we have a one-way function with a trap door. Somebody define one-way function for me. Yeah, pick up the microphone and just go for it.
Hello world.
Hello world. Oh, what do you mean by that?
Like it's getting the value and output. It's getting the value and then just returns
something. Oh, I see. Yeah. So like it takes no arguments or something?
Yeah, like you can say something and it will return it with that. adding hello world and the argument that you will pass.
Okay, yeah. I would say in this case, that's not a one-way function the way that it's used here, but it might be elsewhere, for sure.
You can't reverse it like plain text use key B gives you the same like.
Right, a one-way function, irreversible, right? Those should be synonyms, but they're not. Okay, so here's the truth about a one-way function. That one-way part doesn't mean it's irreversible. It means it's so-called hard to reverse. So it means that this is easy and this is hard. That's what it means for a one-way function. One direction is easy, the other direction is hard. What do I mean by easy and hard here? Somebody.
Just like the amount of operations you'd have to do. So
Yeah,
like doing
yeah.
a million guesses.
Yeah, exactly. Computer scientists when they say easy, they just mean fast. If they say hard, they mean slow. So this is what one-way means, which is confusing terminology. I just want to point that out. It feels like it should be irreversible, but in fact, it's just easy one way, hard the other. Okay, so this is a one-way function, but this is not what we need. This is not quite what we need. This is the first part, that plain text through key A produces ciphertext, and that we can't use key A to go back. That's this part. But if we want to be able to use something else to go backwards, we need some trapdoor. We need some way that this becomes easy if we have a certain piece of information. That's the idea behind what we're doing here. So it's hard unless we've got some information, and then it's easy. It's easy to, I should say, it's easy to encrypt either way. But it's hard to decrypt unless we have this. That's the idea behind this asymmetric key cryptography. OK, cool. So do we want to do this? Let's go one more. OK. So we might do this to solve what's known as the key distribution problem. If we have this issue where I have a secret key I want to share with somebody, I need to send it to them securely, which is a very awkward problem to solve. We'll see how it solves that. And we can also do something called digital signatures with this methodology. Before we talk a little bit more about that, I just want to mention that there are various algorithms for this. There's RSA, there's L-gamma, I think it's pronounced, elliptic curve algorithms. There's a bunch more, too, out there. We're actually going to be going into detail about RSA. But before we do, I want 3 volunteers. Yeah, come on up. Great. All right. So would you stand in a line here? Excellent. Perfect. You're going to be Alice. You're going to be Eve. You're going to be Bob. OK. You're Alice. And here's your writing utensil. Writing utensil, writing utensil. Great. So the idea is that Alice wants to transmit a message to Bob, but it has to go through Eve. And we're going to try and use asymmetric key cryptography to get that message to Bob only. So let's talk a little bit about the rules of the game. So I'm going to give each of them a private key with a different color here. So here's your private key. It's secret. This is secret. This is secret. Cool. They may not all need it, but I'm just giving it so that we can think about it here. And then the way that they're going to be able to send public keys. Here, let me give you some sheets of paper. I don't think you'll need any, but I will give you 2 sheets of paper. I'll give you 3 sheets of paper. So the way that they can use these is you can cover the paper in that color, or just make a mark or something. And you could then put that in front of the message. So if I could demonstrate, the idea is you write your message like, I love Bob. I don't know why that's a secret, but I do. And then you could color on a piece of paper and put it in front of this. And if you do so, and if this paper is blue, then only the person with the blue marker can take the piece of paper off and actually see the message. So the idea here is that, and you can distribute pieces of paper with your color on them. That's your public key. But anybody can put one in front of it. But then you've got your marker, and only you can then see that message. So does that make sense? So now, from the audience, or even from any of these people, how do you get your message to Bob? Here's your marker back. Huh? Green, red, blue. Yeah. Vader, Luke, Yoda. Yeah, please. Yeah, coming up.
If Bob colors on his paper and then Alice asks for a piece of paper from Bob, then she can, or whatever.
Cool, she can, yeah, sure, it's fine. Yeah.
Theoretically. Then they can just give the message to Bob, and then Bob can take off the piece of paper.
Cool, yeah, let's try that out, right? So you have keys. In fact, let's distribute public keys here. So like you could put green on 2 pieces of paper or something and pass it to both of them. You could put red on 2 pieces of paper, and you could put blue on 2 pieces of paper and distribute it to them. Perfect. Incredible. This is my favorite part. Okay, so we exchange these public keys ahead of time, and everybody can have one. It's not, this public key is not meant to be a secret. The marker is the private key. That's the one they keep secret. Okay, amazing. So they now all have paper. So now, did you hear what she said, by the way, to do? No. Okay, I'll repeat it. So you can write your message if you want.
Oh, I did.
Oh, perfect. It's already there. So now you can go ahead and cover your piece of paper with Bob's public key. Bob. Correct. Just the green one. You can keep that one. So this can get sent, right? And at this point, it's going across the internet. Eve gets it. Can you look at it?
Sure.
Well, I mean, you could just lift the paper, I suppose. But are you, like, you don't have a green marker, is what my point is. So, like, you can't, you're not allowed to lift this paper because you don't have the green marker to be able to decrypt it. So you just pass it along. Meanwhile, Bob actually does have that green marker and can lift the paper and read whatever touching message Alice used the Force. Excellent. Amazing. So yes, that's how we can have a secret get sent across here as long as everybody has the public keys. Does that make sense? And does that make sense how that's suddenly different and pretty awesome? Okay, cool. There's one other thing I want to go over. I mentioned digital signatures. Now, this is kind of, in a way, this is a little bit of the opposite idea. I want a message from, let's say, Bob. Or rather, here's how I want to set this up. Bob is going to send a message that says, I am Bob. The message is not a secret at all. But what we do want to be able to know is whether, oh, actually, I need to establish a new rule for this. But that's OK. Whether what am I saying here? Alice wants to receive the message and know that it was sent by Bob. That's the idea. And I need to tell you one more thing that's very interesting about this asymmetric key cryptography stuff. You can also use the private key to encrypt a message. And if so, it can only be decrypted by the public key. So at this point, like let's say you wrote a message with your marker that says like, I am Bob. But the only way to actually see that message is to use the public key. And then it will say, I am Bob. But before it does that, if you use any other thing to decrypt it, you won't see it. So you wrote your message, I am Bob. And then how is that a signature now? Somebody describe that. What will happen if you send this to Alice, say? How can Alice know that it was sent by Bob? Yeah, great. Use the public key. Amazing. So we can try that out, I suppose. But you can send it across. So can Eve, by the way. Eve can verify the message was sent by Bob. But that doesn't really matter. So now you could use which you lost. We need it back. Sorry. Thank you. The public key to actually see I am Bob as expected. So this is a digital signature mechanism where we can know that Bob actually signed this and said, yes, this was legit. Cool. So it's enabled 2 really cool things here. Thank you.
So that wouldn't say I'm Bob. It would say like blah, 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 because it was encrypted with this, right?
Right. It would, yeah, it would say unless you had the green piece of paper, right? Which is kind of I don't know. I couldn't think of a better way of doing this, but hopefully it was OK. Any questions before we continue? All right, thank you. Well played. OK. So we just saw how we can use this to solve the key distribution problem and to provide digital signatures, which is pretty awesome. So now we're going to talk about RSA, because you all are going to be building Caesar shift, one-time pad, and you're going to be building RSA. So, which is awesome, because that's kind of state-of-the-art asymmetric key cryptography. And we can sort of build it in an afternoon. OK. So here's the answer to how we make RSA work. It's math. There's about to be a longer answer, but it's just going to be the math. So, so we're going to go over it. But know that the whole point of this was to get that asymmetric key cryptography working. And this is one way that people figured out how to do it. All right. So here is the gist. People noticed that wouldn't it be nice if we could encrypt a message M like this? So that we do m to the power of e, where e is some encryption key. And here's mod n. Don't worry too much about mod n yet. Equals the ciphertext. And that decrypting looked like this. Take the ciphertext to the power of some decryption key, mod n, and that gives you the message back. So this is not, we haven't answered the question yet. We've just said, wouldn't it be nice if we could do this? Because if we could do this, it means that it's easy to encrypt if you've got E, right? You just take your message, you take it to the power of, if you have E and N rather, you take your message to the power of E, so you just take each chunk, each digit in it or something to the power of E, you mod that by some N, and then you get the ciphertext. And it's hard to reverse if you only have E and N. It's very, very hard to reverse, because trying to figure out what C is here is very, very difficult. You just have to trying to figure out what M is, you just have to keep trying possibilities. You have to say, well, is M foo? And then you take that to the power of E mod n. No, it wasn't. And you just keep trying things. So it's kind of really hard to reverse this, so that's good. But if you have D, it's easy to reverse it. So that's why this is a wouldn't it be nice if. Because if this is the case, it's easy to encrypt with E and N. It's hard to decrypt with E and N. And it's easy to decrypt with D and N. Any questions about that premise? OK, cool. So again, here, M is the original message. E and N make up the public key. D and N make up the private key. And C is the ciphertext. OK, cool. So we have this wouldn't it be nice if. So now we're going to try and get it to be true. And if we just take this as a given, we can actually simplify it down to this here. So we can take, where were we? Yes, we can take C here and just replace it with m to the e mod n. So we can just fill that in here. We get m to the e mod n to the d mod n equals m. So we're just getting rid of the c out of the equation. And it simplifies down to this thing here. So now we're looking for something else. So this is still a wouldn't it be nice if. But now we're looking for just this. M to the power of e times d mod n is m. If we get this, then we get this. So cool. So people were looking for that, sort of. I don't know if this is actually historically true, but we can imagine this story. People were looking for that, and they were like, oh, look at that. Here's Euler's theorem. And Euler's theorem looks like it has the right kind of shape for us, where we have a to the power of 1 plus k times phi n. And if we do mod n that, we get a back, which looks an awful lot like what we have up here. But now I need to talk a little bit more about what's in here. OK, so this was a wouldn't it be nice if. This is an actual formula that exists out there that people were like, oh, we can take advantage of that. OK, so notice there's a lot going on in here. And there's this phi n thing, also known as the Euler-Totient function. I'm sure you've all heard of it. So this phi of n thing is actually simpler than it sounds. The idea is just count the numbers less than that number that don't share any factors with it. So if we were to take phi of 9, we would say, OK, what numbers are less than 9? Well, we have 8, 7, 6, 5, 4, 3, 2, 1. Which of those numbers don't share any factors with 9? Well, that's 8, 7, 5, 4, 2, 1. And so that's 6 numbers total. So you just take a number, you count all the numbers less than it that don't share any factors. That's it. That's what phi n means. And if we go back to this, that's what this is saying. If you take some number a, it can be any number. I could add some unnecessary detail to that, but it could be any number, let's say. And you can then do this. 1 plus any constant we choose times phi of some other number we choose. If we then take mod n, we get a back. So don't ask me why this is true. I can't go into that. But this phi n thing is count the number of primes less than n. And with that, and if we take mod n and we take a to some power, we get a back. That's the idea. And this looks an awful lot like what we need. So if this is the case, if this is an actual formula that works, and this is what we need, what's the next step? Like, how do we figure out how to make this happen? And specifically remember that we're trying to figure out E and D and potentially N. Right? M is going to be the message that somebody sends, but E and D are going to be our public and private key. So how could we figure out E and D? Yeah, right? So we substitute, right? So we say, if that's what we've got as a formula that works, and this is our goal, let's just substitute it. So that means that E times D must equal this thing here. And if we get this to be true, so if we choose any kind of E and D, and we get it to be true that it's 1 plus some k times some phi of n, then we're good to go. Then we can actually make this work. We can take any message to the power of e, the whole other part of it will work. Okay, so our new goal is now this, right? So we've gotten there in a couple of steps, but this is our new goal. Hooray math. And then I want to say that I'm not particularly well versed in math. And then we choose some n, like let's say we just choose 33, like just as an example of how this would work. So phi of 33 is 20. I don't want to do it out, but if we counted all the numbers less than 33 that don't share any factors, we should get that. And now we could just figure out some E and D that work. Any E and D that work, and any K that works. So we get E is 3, D is 7, K is 1. And this works because if we do 3 times 7, it satisfies the equation of 1 plus 20, 21. Okay, so we have just found an example of where this would work, and that means that we could do some message. We could take it to the third power. We could then take that mod 33. That's what our n was. And then we could get our ciphertext. And to go backwards, we would take that ciphertext, take it to the power of 7, and then do mod 33, and we should get our original message back. Cool. All right. So we have to keep that in mind, but then here's a meta problem that emerges. So if we have this equation and we just solve for it in some very, very simple way, then that's a problem. Because remember that E and N are going to be public information. So we need to solve this in such a way that even if somebody has E and N and they know we're using RSA, they can't figure out D, which is tricky. So now we need another thing that's hard to solve here. Just to generate our keys properly, we need to get something that's hard because we need D to be secret. So another wouldn't it be nice if? So wouldn't it be nice if this was easy for us to calculate, but hard for other people, so that D could remain secret? And here's an interesting fact, that calculating phi of n for a given number is actually hard. You kind of just have to take all the numbers less than it and just figure it out, if that makes any sense. You just have to trial and error to figure out phi of n. So it's a very slow operation, but there's a trick, which is that it's easy if we have the prime factors. Okay, so it's easy if we have the prime factors. So that means we should choose 2 really, really large prime numbers, multiply them together, because then we have the prime factors of that number, which means we can easily calculate its phi of n, which means it was easy for us to calculate phi of n, but it would be hard for anybody else if they only have n. If they don't have the prime factors already, it would be hard for them. This is how prime factors fit into all this weirdness, in case you're curious. Okay, so now we're going to say n is the product of 2 large primes, p and q. And that means to calculate phi of n for us, because we have p and q, is really easy. We just do p minus 1 times q minus And by the way, I just want to note here that like if you take phi of a prime number, like if you did phi of 11, it's going to just be 11 minus 1. Because if it's a prime number, none of the numbers below it share any factors with it. So that's easy. And it turns out if you have the prime factors, you can just multiply them. So, so here we just take p minus 1 times q minus 1. That gives us phi of n, which is cool because, just going back for a sec, it's cool because now we can plug it into this equation to figure out and choose an E and D that will work, but that will be hard for somebody else. OK. All right. And the last part is that we throw away the primes just forever. So we generate them just to get n and phi of n, and then we throw them away forever and ever. And that's very, very intentional, because if anybody ever had those primes, it would then be easy for them. All right. So here's the gist again. We're going to generate two large primes, multiply them, which gives us n. We're going to find any e where e shares no prime factors with phi of n. That's a simplification of that other equation. Basically, we need to satisfy e times d equals 1 plus k phi n. And then we're going to find a d where e times d shares no prime factors with phi n. And now we have our e, we have our n, and people can use that to encrypt a message and produce ciphertext. We have our d and we have our n, and we use that to decrypt. It's obvious. It's so obvious, yeah. OK. So I'm going to go into a little bit more detail here about something more like pseudocode of how we do this. Specifically, just getting the key pair. So like if we're trying to generate E and D, again, given some n and phi n that we already have to work with, we're just going to start from E equals 2 and then go up. And we're going to ask ourselves, does E share any prime factors with phi of n? And we can check that pretty easily. And if it says no, then OK, we found our E. And then we start looking for a D. And we start looking for a D, and now we have our E, so we just multiply them and find one that doesn't share any prime factors with phi of n. Prime factors with phi of n. And then, again, so at the end of this, now we have our E and n. And we also have our D that we can use for decryption. Any questions about the crazy math here? Yes, some questions. Any particulars, though? OK, just like lots of them. Yeah, just OK, great. Amazing, yeah. So cool. So I just wanted to go over the details. And I want to say that this is definitely a little involved. But what we've just gone over in the course of 10 minutes with this math or something is RSA. And that's pretty powerful. And it's powerful because, getting back to the big picture, we can do this. Where we now have this trapdoor, and this whole system can work for us. So I do want to mention that like the specifics of RSA are a bunch of math, and probably the big thing to get out of today is not the exact math that goes behind RSA, but this concept in general and what it means. We went over the math, and we're going to be building RSA so that you can demystify it a little bit, because this asymmetric key cryptography stuff probably feels like math. In fact, I kind of think all of cryptography is this fun math, fun magic trick, right? Where you do it right in front of them, and then you send it somewhere, and it's magically decryptable. It's like all happening publicly. It's incredible that that can work. So I think that's really cool, and I want to make sure that comes across. All right. The workshop we're going to be working on, you're going to be building Caesar shift, one-time pad, and RSA, which is cool. Hopefully it'll demystify it a little bit. Any questions before we get started?
It's a little bit off the topic, but
Sure.
There is like types of keys when you can just like, they're like created asynchronously. So for example, I can access my computer and go in some program with that key, and it's constantly updating while I have it, and it's constantly updating on the server or where is that key exists.
Yeah. Are you talking
So
about, is this like a password manager program too or something where like?
It's kind of. It's just for like big financial companies. They create these keys, so like their workers can always access it wherever they are.
Got it.
I don't know what is that. That's why I'm asking.
Yeah, sure. Yeah, I don't remember what goes behind those, but I think so correct me if I'm wrong, but the question here is like, how can we not just generate one key, but some sequence of keys that's like constantly changing over time, that corresponds to some other key that's constantly changing somewhere else? So I don't know the answer to that, though something in my head is telling me it has to do with the elliptical curve algorithms. I think those are commonly used here. I just don't remember the specifics. And I could be wrong on that, but that's just where my brain is going. It's a great question. Cool. Any other questions? RSA. Oh, man. Going through the math. All right. Okay, that's it. So get started with parts 3 and 4. We're going to meet back here at 5:30, which should be in about 2 hours, to try and review that stuff. Good luck, and use the force. Oh, really? Oh, no. It is on, apparently. I don't know. All right. How you doing? How is everybody out there? Make some noise. Wow, that was an amazing sound. Could somebody just walk to the mic and do that for the remote students? I can reproduce it a little bit. It's like, it was a groan. Incredible. So, okay, let's talk about some encryption stuff with Caesar Shift, with one-time pad, and then with RSA. If you have questions, shout them out now or as we get to the stuff, whichever you prefer. Cool. Caesar Shift, tell me about generate key. What does it take in return? What's the key in our Caesar Shift? Remind me. Everybody's like, I'm looking. Give me a sec.
The key is how many digits to shift it, or letters.
Perfect. Yeah, the key is a number, and generate key doesn't take any arguments, right? In this case, and the key is just going to be a number between 0, no, that's not shifting it at all, 1 and 4095. Mind games, yeah, you just don't shift it. Wow, weird. Okay, I love that idea. So, yeah, it's a postmodern encryption scheme. Yeah. Okay. So, and this should be good for what we need. And this is inclusive. Yes. And encrypt here is going to take our key and our ASCII plain text. And it's going to return some base 64 ciphertext. How do I want to do this? Yeah, I'll do that. Base 64 ciphertext. Cool, and we're going to get there in stages. And the base 64 ciphertext is, again, just so it's human readable if we decide to console log it or something. So the idea behind Caesar Shift is we just take the ASCII value that we've got. By the way, this is fake ASCII, just so you know, this 4096 base thing, just something I came up with. It's not, ASCII is weirdly defined, but it's sort of the first 128 of Unicode at this point, but it has a weird definition. I just want you to know that this is not quite ASCII. But so we're going to take our ASCII plain text. We're going to get the digits out of it. So this should give us an array of digits representing those ASCII values. Then we can map down that. Here, let's do an arrow function. And for each digit, we can shift it by adding the key. And then we just need to take that modulus 4096 in case we go over the edge so that we wrap around again. Okay, and this should come back with cipher digits, so to speak. And then we can take these things, ASCII, what am I doing? It's going to be ASCII from digits on this thing. And then we're going to, and this is going to be our ASCII ciphertext. And then finally, our base 64 ciphertext is just ASCII to base 64 of that thing. So a lot of conversion between various formats of data here, where we've got like ASCII and we're getting the digits, or we're getting it in base 64. And I think that's kind of an awkward thing about this workshop, but sometimes an awkward thing about working with low-level information in general is a lot of this data transfer. So I've considered trying to abstract it out, but it seems like it's probably a useful step to go through just in terms of practice. So I've left it in there. You can thank me for all that weird conversion that you have to do everywhere. All right, part 3, let's put these in and see how it's going. Yeah, see what happens. Boom, errors. ASCII is not defined. That makes sense. Let's go back to here. Oh yeah, I didn't pull in here. Let's do this. Let's pull in our like ASCII utility, like we would hope. Okay, cool. And now digits for each is not a function coming from ASCII JS line 16, coming from Caesar shift line 14 here. ASCII dot from digits, ASCII plain text. Oh, 2 digits. I can thank me for all this weird conversion we have to do. Okay. Thank me. And now we can go on to this one. This one's the same idea, only we're going to have base 64 ciphertext here. And we're kind of going to do this backwards now. So we have our base 64 ciphertext. And so we go back to ASCII ciphertext now with it by doing base 64. I got this to ASCII. Cool. Once we've done that, we then reverse this part. So we have to get ASCII ciphertext needs to be digitized. And now we're back there with our cipher digits. And now if we want to get back something like plain digits, which we didn't really name up above, that would be mapping down our cipher digits. So tell me about the inverse here. What do we do?
You return digits minus key or digit minus key.
Yeah,
And
cool.
then if you want to care about the off chance that you go below 0, you have to
Mod by 4096. Yeah, though I think we'll run into another issue still. I hope so, at least. But yeah, we'll deal with it when we get to it. Yeah, thank you. Great. So we have the same idea, only minus instead of plus. Just shift. I think of it as left, after having shifted right when we encrypted. Okay, cool. So now we take those plain digits and we can get our ASCII plain text back by doing ASCII from digits. These will be plain digits. We can return our ASCII plain text. And just for completeness, I am actually going to put our plain digits up here too. So it looks like that. And then we do plain digits.map. Now we have this nice symmetry going on here, where one does like the exact reverse order here. I like it.
Can I ask a question?
Of course.
Will that mod actually save us if it shifts like below 0?
No, it will leave us hanging. Yeah, it will not help us. In fact, let's see that happen. I think we'll see that happen in one of these specs. Let's see if we see it happen in one of these specs. Oh, bummer. Yeah, so this wouldn't actually save us. Huh?
I don't think we had the mod effort for the test spec.
Oh, okay. So yeah, so let's pretend we had gone negative. You never want to go negative. Always stay positive. So 1 minus 10 or something, so we end up with like -9. If we were to do this mod 4096, we actually still end up with -9. So here's another trick that I like. If our original thing was we had 1 minus 10 and we were doing that, we can just add 4096 to this always before we mod it, and then we'll end up circling back around. So that's one neat trick that can work here. Just always add 4096, and that means you're going to be greater than 0 by a big margin. In fact, you're almost always going to be greater than 4096, but you're going to get the remainder after it, so it doesn't really matter. And if you end up less than 4096, everything's fine still too. Right. So if somebody has a malformed key that's not within the expected range, like we would have a different problem. Yeah. Good point. Okay, cool. So that's Caesar shift. Any other questions on that one? Okay, cool. Let's do on-time pad. Actually, do we want to do that? Let's refactor this a little bit, just for fun. So this will be something like, I'm just going to make an internal method, and I'll specify that with an underscore here. I'll call it something like shift1. Because I'm noticing that, actually, you know what? Shift text or something. I'm noticing that like there's sort of a similar fundamental lot of stuff going on here, where we're taking some ASCII, converting it to digits in both cases, mapping down it and doing an operation where we're adding some key. Here we could think of adding the negative key or something, and then getting it back into ASCII. So let's pretend we're going to get the key here, or the shift value maybe, and then the ASCII text. And we can do these parts. And we won't know if this is encryption or decryption. It's actually going to be useful in both here. But we'll have digits. And we can map down that, where for each digit we return something like this. This should cover both cases nicely. And here, instead of, I'll just do plus key, and we'll put in a negative value if we need to. This should come back with, I don't know what to call it, transformed, shifted digits. There we go. And then we can get shifted text as ASCII from digits. Shifted digits, and return that. Okay, so the reason I'm thinking this will be useful is I think we can jump past a lot of stuff now. So ASCII ciphertext could just be CSS. Everybody's like, no, not CSS. Okay. Shift text by key, comma, ASCII plain text. So we can jump straight to the ASCII ciphertext. And down here, we should be able to jump straight to the ASCII plain text from the ASCII ciphertext. Yeah. And this will now be shift text by negative key ASCII ciphertext. So we're using the same thing to go like forward and back here, which is kind of cool. And we're drying out our code a whole lot. And it's totally breaking. ASCII plain text is not defined. I don't know why it's so upset. Could have just told me. ASCII 14 here. Oh, right. This is just called ASCII text here. Yes, because we don't know whether it's plain text or not. And key is not defined. Oh, right. I decided rather to call it shift up here, just because we didn't know if it was exactly a key. Okay, cool. Excellent. Let's go on to one-time pad. One-time pad, generate key, same idea, takes nothing. What does this one return? Actually, it does take something, doesn't it? I'm a liar. Yeah, it takes a length and generates what?
String of base 64 characters.
Cool. Which we kind of already got. In fact, I think we could probably just do this. Probably just set it equal, and I think it would work. Let's see what happens. I actually have never tried doing this in particular, so we'll find out. It's different each time, produces random base 64 string. No. Oh, this is cute. Expected spy to have been called. Huh. Oh, this is maybe really interesting. I think it actually works, but the specs won't be able to recognize that the way they're specified. Because we're spying on the method that's getting called. I'm not sure how to. Yeah, I'm not sure how to get that across effectively. But spy on works in a slightly weird way. So this should actually work though otherwise. I'll just exit this for now. I'll do that cheating thing. And we'll see if it actually pans out when we go through the rest of one-time pad. Okay, tell me about encrypt and decrypt. What do they take? What do they return?
They both take a key and a message.
Key and message. Great. Cool. I'm going to call it ASCII plain text. And I'm going to say this one is base 64 ciphertext. But they're both messages. That's absolutely a fair assessment. I'm just going to give them a little bit more descriptive names. Excellent. So they actually have, and in fact, all of our encryption and decryption should have the same kind of pattern here. Key, comma, plain text. Key, comma, ciphertext. OK. So let's go through here. And we're going to do a very similar operation as to Caesar shift, where we like convert it into a certain format. Only this time we're going to XOR it with digits from the key. And the key is actually base 64 already. So we should be able to say something like key digits equals ASCII.2, base 64, 2 digits, key. OK, and we will also convert this ASCII plain text to base 64, giving us our base 64 plain text. OK, cool. And now we should be able to go down the base 64. Let's actually get the base 64 digits to base 64. Actually, I'll just call them plain digits. Is our base 64 plain text. Base 64, 2 digits. OK. Plain digits, we map down it. Plain digits map for each digit and index. We can get the corresponding key, digit, key, digits, index, and then we can XOR them, which it turns out is surprisingly nice. We just do digit, caret, key digit. Cool. All right, this comes back with something we'll call cipher digits. And then we should convert these cipher digits back into base 64. So base 64 ciphertext. And we can return that. This sounds good to everybody? It's going to work? Or is it? Did I put a bug in there? Even I don't know. It's that, I have to do that every time just in case I put a bug in. It can seem like I did it on purpose. Oh, yes, that bug. Yeah, that one. So I have a syntax bug. My favorite, the most delicious kind of bug, in my opinion. Here we go. OK, good. Nifty. So now let's go on to decrypt. And then let's do something fun with it. So let's see. Inverse, exact inverse of everything. So const cipher digits equals base 64, 2 digits of our ciphertext. So that gives us our cipher digits. Now we want our plain digits, which is base 64. Wait. Oh, sorry. It's cipher digits map. We go for every digit. Ooh, we're going to need something a little bit up here. The same idea as this one. We want our key digits. And then for each one, we are going to get our key digit from the index and XOR it with the key digit. Anybody notice anything odd going on there while I continue here? Not problematic, just interesting. I'm thinking about this one here and this one here. Cool, and again, we can just convert to base 64 plain text. And then finally, we can get our ASCII plain text by doing utils base 64 to ASCII. Cool, and we have the exact inverse of what we just had a second ago. Let's return ASCII plain text. And let's put our decrypt specs in. And you know what, because I'm feeling ambitious, let's put all of our one-time pad specs in there. So has anybody noticed anything about these two?
So both of these maps are completely identical. So if you just change them to the function from outside.
Yeah, this is utterly identical. Perfect. This is just taking a digit and a key digit and XORing them, and that's it. And in fact, just like before in our Caesar shift, we can probably take like this sort of, there's a lot here that's repeated in general, so we might make a one-time pad XOR text. Sort of the fundamental operation that's happening in both of them, which will take the key and it will take the ASCII, actually it'll just take the, in this case we're using base 64, it'll take some base 64 text. And it doesn't know if this is plain text or ciphertext. That's not in its purview. But let's go ahead and move, let's like copy some of this up. So we can get digits from this base 64 text. Then we can get our XORed digits by going down our existing digits. Ooh, right, we need the key. Almost forgot that part. So we can get our key digits as well. And then we get our XORed digits, and finally we can get our XORed base 64 text, which will look like base 64, oops, dot from digits, XORed digits. Okay, beautiful, XORed base 64. So this is very common to both of them here, and we can do a similar operation of removing a lot. So let me look at the right spot here. Base 64 plain text straight to base 64 ciphertext. So I think all of this, and in fact this can go away too. And we just end up with one-time pad, XOR text, called on the key, and the base 64 plain text in this case. And down below here, we can get rid of all of this, and we can jump straight to the base 64 plain text by doing one-time pad, XOR text, key, and the base 64 ciphertext this time. Same operation, ciphertext or plain text is what we pass to each of them. I really love looking at this because it's so cool. Like these boil down to like almost the same operation in the center. It feels like how is the encryption decryption even different? There's like only this slight difference now going on. Let's try it out. I should do that before being all grandiose about it, because inevitably it will fail. Any questions looking at one-time pad, looking at Caesar shift? Cool. Let's go on to RSA then. Yeah, let's do it. Awesome. And there's quite a good bit to cover in RSA, and I actually want to jump over to the specs for this one. Select key pair already has a lot going on in it, and there's definitely this very, very useful link here. Or the slides, which I should have put in your repos as well. By should have, I mean they actually were in there. I don't mean I failed to, I hope. And so we've got this here. I like these instructions. So we're going to assume that two large prime integers are coming in for us. And now we're going to go down these steps of trying to find E and D and N. just as specified by the math that we went over, and of course all understood perfectly during the presentation. Yes, everybody, even Patrick. Okay. So let's keep this open. I'm actually going to make this a tad smaller so that we can see more of it. All right, that's good enough for me. So let's go back to RSA. So our select key pair, what does it take? And what does it return? Please.
So it takes 2 prime numbers.
2 prime numbers. Cool. Prime A and prime B.
And returns pair of 2 numbers.
Okay.
Which are E and D.
Okay, cool. Okay, it returns E and D. Great. Excellent. And that's what they're called over here. So let's go ahead and get N. How do we get N, by the way? Multiplier primes. That's how we've defined it to work. And in fact, utils also has an Euler's, or I think just a totient, thank you, a totient function, so that we can get the phi n of n easily. But in order to do it efficiently, we're supposed to pass it the prime factors here if we've got them. So that's prime A and prime B. By the way, you could also, if you just know the trick, you could also just do prime A minus 1 times prime B minus 1. This is fine too, because it happens to have 2 prime numbers, and this is how you put it together. Okay. So, but this is more generally how we might do it if we were just using the totient in general. Okay. So now I think comes the weird part where we need to select an E. So it says it has to be greater than 1 and less than phi n. So let's start E off at 2. And we need to keep going until the greatest common denominator of E and phi n is 1. Okay. And we actually also have utils.gcd. So let's go ahead and do that. You know what? Let E, and now we do a for loop for E equals 2. While it's less than phi n, we increment it. And if we get to a point where the greatest common denominator between E and phi n is 1, we can break out of this loop. And that's our E value. That should be good enough to find it. And now D is a little stranger, but not that weird. So at this point, now we want to find D. And we want to find it between 1 and phi of n. So actually, I'm going to do this one a little differently, I think. But now we need E times D. And here's where we get this sort of odd equation. But this is also saying now that E times D, their greatest common denominator, we can do modulus, I suppose. But E times D mod phi n should be 1, which I think is actually just another way of saying the greatest common denominator. But that's OK. So let's go ahead and do another loop now. I'm actually going to start D out larger. Yeah, so I'm gonna have D start out at phi n minus 1. And this is because I want our D value to be large if possible, because this is our private key. And if it's small, it might be more guessable. So then we're going to say keep going while D is greater than 1 and do D minus minus. Now if, I think this should be utils. Now if E times D mod phi n is 1, I think this is now when we've found our D and we can break. And then at the end, we should just be able to return ED. That's what I'm thinking. And this is just following the outline we have here. So any questions about this? I'll start putting the specs in to see if it's actually going to pass or not. But I'm curious if people have questions. Cool. Yeah. That does it. And again, this is all so that we can set up this equation so that it will work. That we can pass in any x and take it to the power of E times D mod n and get x back. That's the whole point. Because if we have that, we've got our RSA asymmetric cryptography system. So generate keys, this is, I think, a little bit different. Like this key pair is just E and D, as it were. Generate keys here, you can imagine this is our public and private key. So our public key actually has to contain not only E, but also N, so that somebody can do that encryption step. And our private key has to contain D into N. So it's the key pair, you can imagine just these two things, is one word for it. But we also now need our public and private keys. So this is going to take prime A and prime B. And so this N, I'm going to call this N our modulus, because that's what we're going to use it as. So again, that's prime A times prime B. And now I'm also going to get E and D by doing RSA select key pair prime A prime B. Cool. And now with this information, I'm going to return an object that says, I think, public and private. And in general, we want our public key to be the smaller one, which will happen to be E the way we've set this up. But funnily enough, we can actually flip them. That's an interesting thing about RSA and about asymmetric encryption. We could give somebody D as the encryption key and leave E as the decryption key, because they actually both work to invert each other. But we want to go with the smaller one for our public key, which happens to be E. So somebody remind me, there's some sort of syntax here like that. Is that correct? Okay. And similarly, it's something like this. Let's see if that's the right idea. Let me put these specs in here.
Oh, wait, it might have been the other way around.
The modulus first?
Yeah.
Okay. Cool. Do I have a fancy way of reversing this? Sort of. Nope, I don't. I shouldn't have tried. All right, let's just undo this. Modulus plus E modulus plus D. Okay, cool. And one last thing I'm going to change here. Oh, by the way, I very much glossed over the destructuring I'm doing there. Is that weird to anybody? Does anybody want to talk about this const array bracket E comma D? It's okay if you do. It's interesting stuff. You want to do? You want to? A little bit. Oh, you don't? Okay. Okay, great. Everybody is perfect with ES6. Sure. Just go over just in case. Okay, good. So, so this is a lot like saying, so key pair equals. We don't have to use this destructuring. It just saves us the headache of doing something like this. Const E equals key pair 0. D equals key pair 1. So if you ever find yourself doing something like this, there's this fun thing in ES6 you can do, which is basically telling it, hey, const, and then you provide these array brackets to say, the thing that I'm assigning from on the right-hand side is going to be an array. And I want E to be the first thing from that array, and I want D to be the first thing from that array, the second thing from that array. 0th or 1th, I guess, if we want to use those terms. And so it's a very good shorthand way of doing lines 28 through 30. So let me just leave that here and say equivalent to the following. Awesome. And just some more ES6 fun, we will use template strings. Because why not? Because we can. But of course, we do not have to. It can just make things a little easier to read. I don't know about you, but once you get the hang of template strings, like I find this a little bit easier to parse. I can be like, okay, something colon something else, instead of looking at all the pluses and trying to figure out what fits together where. Okay, cool. We're on to encryption, which is where all the crazy magic happens. Let's do it. Okay. So somebody tell me what happens. So what do our encrypt and decrypt take? Same thing as before. Key. What am I doing? Not prime A. ASCII plain text, and this takes key and base 64 ciphertext. Okay, cool. And what do these do? What's the fundamental operation that's going to happen on each digit when we get this ASCII text converted into its ASCII digits? Palin digits. I don't know what that would mean. ASCII 2 digits. Still looking for an answer to the original question, by the way. What are we going to do to each of these plain digits? So everything's going to work, right? Probably not, yeah. Actually, I'm curious what we'll even see. We'll probably see unexpected token question mark. I don't know, something like that. There it is, unexpected token. It actually looks like it's saying unexpected token. Yeah, because, OK, we need to fill this part in. And I won't leave it as a rhetorical question. What do we do here? Yeah, please.
Well, we have that nice helper function, the modular exponentiation.
Good. So utils dot modular exponentiation. Okay. Yeah, but like, what do we? I mean, what's like the fundamental operation that happens in here? I guess it is kind of that, I suppose. I think that's fair. I think that's fair to stick with that. Here, let me go to what this is saying too. So again, this is if we want to encrypt, we take the message, and you can imagine this is each message digit. We do this to the power of e mod n, and then we get back a cipher digit. So we can imagine that that's sort of like doing. We take this digit and we return digit math dot power of this digit to the key, part, the variable part of the key. Let's call that the exponent. We should actually probably grab that. So our modulus and our exponent come from the key. We can split it and map those things to numbers. So we end up with the two strings representing the two parts of our key. Then we convert those to numbers. That's fine. And now we have our modulus and exponent that we need. So it's sort of like doing this. Does anybody know why this is going to be a problem? Line 45. So we're trying to take some digit to the power of exponent and then modding it afterwards. We could try it. You want to try it out and see what happens? OK, great. Let's do it. Let's head over here. We have our encryption in, so we can run our test. Oh, one thing is this. The test expects us to use utils.modular exponentiation. We can turn that off. Where is that? Here. Yeah, you can. I mean, we'll see that you did that, though. Blah, blah, blah. Expected function to be a SPI. Oh, I see, yeah. Oh, but we probably won't even see a failure then yet until we get to a little bit later, because I don't think it'll care. But let's do an example then. Let's go into Node and do like math.pow. We might end up with a cipher digit of, I don't know, 62. And we're going to take that to the power of, the exponent here will be E or D. Let's say it's 21. What is an example? Do we have an example somewhere to go off of? I think we do. Oh no, it just asserts that they equal something. Whatever, let's just pretend here. So it's 21. Then we do modulus 187. 75. Let's make this slightly larger. Okay, cool. So here's the problem that happens. We can't really get too large with this kind of math. If we do this step by step and literally try to take 62 to the 211th power, we're going to have a really big problem. That won't work at all. So instead, there's actually a method for doing this. If you know you're doing mod followed by exponent, there's actually a neat trick behind it, which you can go look at in the utils. That's what this is doing. There's this sort of stuff you can do with the, you can get it into base 2 and start accumulating a value, but it will be possible suddenly. And this trick is just an interesting math trick we can do to make it work, that's all. But it's fundamentally the same idea as this. This just won't really work step by step. So okay, so let's use utils modular exponentiation, and we pass that the digit, the exponent, comma, modulus. And it will do that fancy math for us that puts it all together. And that means we can probably unexit that spec as well. Here. Cool. Let's go back to RSA, and let's do decrypt. So decrypt is going to look like our previous decrypts, where we say, OK, we want ASCII ciphertext. ASCII ciphertext. And we can get that by doing utils ASCII to base 64. Wait. Oh, other way around. Base 64 to ASCII on our base 64 ciphertext. Then we take that thing and get cipher digits out of it by doing ASCII 2 digits, ASCII ciphertext. Then we take that thing, and just like we're walking up here, we now get plain digits, which I'll leave as that. And then we walk one higher up, and we should now just convert these plain digits back into ASCII text. ASCII plain text by doing ASCII.from digits, plain digits, and now we can return that. Okay, so what goes here then? What's our decryption step look like in RSA?
It's the same thing, isn't it?
Yeah, it's kind of the exact same thing. It's kind of cool. So it is in fact the exact same thing, just with plain digits swapped for cipher digits. We go down it, and for every digit we get, we take it to the power of the exponent and the modulus. So let's copy that down as well, so that we get our modulus and exponent from the key, which is a string, by splitting it by the colon and getting an array of two things, and then mapping both of those two strings into numbers. And let's see what happens. So let's throw all of our specs in. It's a spec party. One pending. Oh, that's the one I took out because I'm cheating a little. Well, not cheating. I'm being succinct. I'm just doing this on line 9. OK, cool. That's RSA. We did it. Like, that's a very, very advanced crypto system we just built. There's some pieces missing, right? Like, we were like, assume 2 large prime numbers are coming in. And, you know, there's some math behind finding random prime numbers of a certain size. But that, like, assuming we had that, this would work. And this would work great, which is really cool. This is really cool stuff. And again, like 50 years ago, this was science fiction, and now we can code it in an afternoon. So, and hopefully it demystifies a little bit of what's going on behind the scenes. And so when people talk about asymmetric key cryptography, you can think, oh yeah, there's, and they're talking about RSA, you can think, oh yeah, there's modular exponentiation going on behind the hood. And I remember we're getting the key by doing some fancy math with prime numbers. And I remember this thing about one-way functions. That all will be great. Let's do one last step of refactoring, just like we did for these past ones. Let's make RSA dot mod exponent. I don't know what to call it, but mod exponent text. Cool. And this will take, let's see, it can work with ASCII plain text and a key. So we're going to want to get the modulus and the exponent out of the key. We're going to want to get digits from that. This is actually just ASCII text. We don't know if it's ciphertext or plain text. And then we can take this part out as is. This will be mod exponented digits. That's a word now. Digits, map, blah, 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 exponent modulus, same operation for both. And then we can get this back into mod exponentiation as exponented. Mod exponented. Exponented? I guess it doesn't matter if I'm making it up. And that's ASCII from digits. Mod exponented digits. Mod exponented ASCII. If it ends in ASCII, it's mod exponented. If it ends in digits, that's the rule I'm making up. It's mod exponented. Yeah. Okay. So there we go. So we've got this core thing that we can now rip out of here. In fact, done. ASCII ciphertext can come straight from the ASCII plain text now, and the key, as long as we call RSA dot mod exponent the text on ASCII plain text. And down here, same idea, only we need to get the ASCII ciphertext first, and then we can do this. So now we can do RSA mod exponent the text, key ASCII ciphertext. I find it neat that even though this is an asymmetric cryptography, the algorithm has this symmetry hidden in it, which is neat. Cool. Questions? Yeah.
So the larger the prime numbers, the harder it is to decrypt?
Yes, exactly. So the whole reason we're selecting a key pair this way and using the totient and everything is that if somebody else were to try and figure out D, and they only have E and N, they first need to calculate phi of N. If you remember that fundamental equation we have somewhere, actually I don't know if it's on here. Let me pull up the slides for a sec. If I didn't kill them already. Okay, where was it? I think here. Like if they know we're using RSA and they have E and N and they want to calculate D, they're first going to need to get phi of N. So, and in order to do that, the fastest way to get phi N is to just factor N. But N is the product of two very, very large primes. And the best way to factor a number, by the way, sort of, is just to start guessing, which takes a long time with a large number. You're just like, is this a factor of it? No. Is this a factor of it? No, etc. You start, so if you know it's 1,000-bit number, then you just start with 1,000 binary digits, and like you start with 1 followed by a bunch of zeros, and then you just start counting up. There are actually more efficient ways of trying to find things, but you can imagine it's that kind of slowness of just trying literally every number that's 1,000 bits long, which is a lot of numbers. Yeah. So it makes it slow for anybody to find D given E and N. The other thing that was slow is this. The other thing that's slow, which is good to know about, is this modular exponentiation logic. Reversing that is also difficult. So regardless of if you're trying to find D at all, like let's say you don't care. You just care that given C, which you have, and N, which you have, and E, which you have, that you can find M. That's also difficult to reverse. So there are actually two difficult things to reverse going on in RSA. One of them is the encryption step itself, this thing here. Another one is kind of the key generating algorithm. Great question. Any other questions out there? Looks like not. Cool. Okay, I just want to wrap up to remind you all that these are the big takeaways. Great job on the workshop, by the way. I saw a lot of awesome stuff out there. Yeah, you have a question. Yes, please do it.
Yeah, in the utils prime factors, the n is equal to math floor mass power n of 0.5.
Yeah.
Is it like kind of
Oh,
square root of?
Yes. Yes. If you're looking for the prime factors of something, you can jump down to the square root of that number and go from there. Because you know it's not going to be larger than that. Yep. Yeah. Good question. Yep. Cool. Yeah. So again, awesome work out there. This is a tough workshop. Cryptography is really cool, but can be challenging. But these are the big things to remember. That randomness is this fundamental concept in information theory, in computer science, and especially relevant in cryptography. We see it playing out in a lot of ways. Then there's hashing, which is really, really useful for things like password storage in databases or password storage in transit, things like that. And also useful for message authentication, as well as things that aren't cryptographic, like identifying a bunch of folders with a git commit ID. And then there's encryption, which is really the opposite of the stepchild or something. It's the favorite child of cryptography or something. Like when we talk about cryptography, this is kind of the heart of it. Encryption, which is split into two flavors now. Symmetric, where the key we use encrypts and decrypts, and asymmetric, where we have two keys, one that encrypts and one that decrypts. That's the big gist. Yes?
Is this the reasoning why there's like bounties out there for finding like largest prime numbers? Sort of way back to this.
That would make sense, though I don't know why, I don't know who you would, it seems like if I were wanting to be secure, I wouldn't want to get somebody else sending me their prime number because I wouldn't trust that they'd kept it a secret. But also that you can actually just generate large primes in polynomial time. So like, I don't think, I can't, but maybe, I've heard that too, and I feel like I've heard it related to this, but now I can't place it given what I know. So I don't know. Yeah, it's a great question.
Electronic Frontier Foundation has an award for it. I just found, yeah, but I don't. It's not like a company. It's just like you've made a good algorithm that made a super, super long prime, like in the millions and hundreds of millions of digits and things like that.
Cool.
Yeah. So can you also please talk about like the quantum computers and the primes?
Yeah, cool. I was actually gonna say, does anybody want to talk about that at this point? We got a couple minutes left, and we can talk about some interesting stuff with quantum computing. So who know, like, Raise your hand if you have read anything ever about quantum computing. Okay, cool. So let's talk a little bit about it, which is that in an ordinary computer, okay. Elliot, you got this, right? Okay, great. It's only Joe? Joey and Sean. Hey, Joey and Sean. You're going to learn about quantum computing. Okay, so in an ordinary computer, right, we have a single bit that is the fundamental unit in computing. And not even an electronic computer, just the theory of computing. You have 0 or you have 1. And then if you have like, let's do a 3-bit computer, you've got these possible states. It's either 0, 0, or 0, 1, or it's 1, 0. Wait a sec. I'm changing this to 2-bit. Okay. I just don't want to write them all out. Or 1, 1. Okay. Now let's talk about a quantum computer. You have qubits. And it's based on a fundamentally different idea, which is that you don't have 0 or 1. You have 0 and or 1 in this weird quantum superposition way. So this by itself is just, quantum mechanics is weird, right? And this is just a hard thing to talk about. But you can imagine that it's sort of in both states, right? And it's sort of representing multiple states in a way. And here's where it gets crazy, though, because if you have a 2-qubit, that says qubit, believe me, quantum computer, then it's 0, 0, and or 0, 1, and or 1, 0, and or 1, 1. So this is how it scales. As you start adding qubits, you actually start exponentially adding simultaneous states instead of just possible states that you could be in at different points in time on an ordinary computer. You're actually in many simultaneous states at once. Is an okay way of thinking about it. That's the point. This is a little hand-wavy, but it helps. And okay, so that means that you can imagine quantum computers are almost fundamentally parallel. It's like they're representing parallel states. And there are certain operations, there are certain algorithms that they can do much more efficiently. One of those is Grover's algorithm, where you can search through an unsorted database. So imagine that you had a phone book and you were trying to look up somebody's name by phone number. Ordinary algorithm, ordinary computer, you just start looking through the whole thing, right? One at a time. And eventually you find it and you say, okay, that's their name. But with 1 million entries in that phone book, it's going to take you on average 500,000 guesses to find it. So we say, and it's O of n time, right? We have to look through, we have to scan all the whole table, the whole phone book. In a quantum computer with Grover's algorithm, you can get that in O of square root of n time. So 1,000 guesses instead of 500,000 guesses. And it just gets more dramatic as it increases, of course. And this is sort of because you can tell the quantum computer to try a bunch of things at once. And then the answer is going to become more likely after one step of that. And you do another step where you try a bunch of stuff at once, and the answer becomes even more likely. And it turns out you have to do that about square root of n times before the answer becomes likely enough that when you measure the quantum computer, it collapses to the right answer. Okay, weird stuff. But I use Grover's because I think it's easier to talk about than this next one, which is finding the prime factors of a number. Quantum computers are also faster at finding prime factors using something called Shor's algorithm. And they can do that in polynomial time. So that means that with good quantum computers, RSA is broken. It's not a good crypto system at that point. And that's interesting. It's very interesting to note. And I do want to say that just to ease your mind a little bit, the largest quantum computer that I read about recently was somewhere around 20 qubits. So they're pretty small, and it's not clear that they can be scaled effectively or not. So nobody has actually showed a good scaling mechanism for getting this level of parallelism up to many qubits. There are sort of fundamental problems to consider. And I'm not an expert by any means, But from what I've read, it's not a solved problem either way. My guess is that we'll get there, just because we kind of always do. And I do want to say that at that point, with quantum computers out there, there are actually quantum cryptographic algorithms that will be able to replace what we currently use. And there are other algorithms out there that just don't rely, like we talked about elliptic curves and LGAML as other asymmetric key cryptography systems. So I don't remember about both of those, but there are asymmetric key cryptography algorithms there that are not broken by quantum computers, that are ordinary algorithms, not quantum computer algorithms. So suffice it to say, we're probably okay. Which is, I mean, global warming will get us first, Or Skynet, there you go. Or Steve Skynet. I don't know if anybody knows Steve. He's just a programmer. I don't know.
I just want to add that
Yeah.
I think I read like a few months ago the article like at MIT, like when the actual one of the professors, he went here he went to Google's office, and like they have a laboratory where they're developing. So they're actually kind of not far from actually building the really good, like large-scale quantum computer. So
Yeah.
that might be the case pretty soon.
It's true. It might. Though I'm guessing what they're talking about is the D wave. That would be my guess. There's this 1,000-qubit quantum computer out there, but it's not exactly the same. It's a sort of different type of quantum computer. It's sort of like an analog quantum computer as opposed to a digital quantum computer, which is sort of more what I've been outlining here. And that's not to say, so it might actually change the game fundamentally. You might be right. But I've also read things out there saying that it might not. And it might just be a like quantum-ish computer, but not quite the level that's going to change the game fundamentally. We'll see, exactly. I don't know. I really can't say.
They also operate at like almost absolute zero, right?
Well, yes. Actual quantum computer hardware right now is like some sort of weird, it's very, very strange. It's very, very large, and it has to be super cold. You can imagine, I try to imagine that the quantum states are like really, really fragile, and so that's why it has to be so cold. Because you have to like keep everything very exact.
Just like how they created this qubit.
Oh, cool. I don't know. I've read about some hardware before, but
Like almost absolute zero. So right now, I think the only one place where it's being successfully developed is Bell Lab.
oh, cool.
So it's like, I don't know. That's the only guy who can actually do that successfully.
Yeah, that sounds really neat. I am super excited about quantum computing in general. I'm very curious where it's going to go. Yeah. Cool. So that's cryptography and a little more. Have a great night, everybody. Yeah. Yeah, you're welcome. My pleasure. What is it, 6:35?